Hello everybody! Welcome to our open online course on Discrete Mathematics. I'm Dominik Scheder. I'm an assistant professor here at Shanghai Jiaotong University, and it is my great pleasure and honor to introduce you to this exciting topic. So this is our first lecture of this course, and I will use it to tell you a little bit what discrete mathematics is, how it differs from other parts of mathematics you might have seen before, and also why we study it, what its applications are. First, instead of giving you an abstract explanation what discrete mathematics is, I want to show you a concrete example that nicely illustrates certain key concepts. My example is a puzzle that some of you might already know. So in this puzzle we have a board which is divided into 8 times 8 squares. Now suppose you take a saw and you saw off 2 opposing corners, like here and here. So now we have this chessboard with 64 squares, but 2 are sawed off, so we have 62 squares. Now we have these domino tiles, and using these domino tiles we want to cover the whole board. But of course every tile must be put on the board orderly, covering exactly 2 squares. So we could do it like this. We continue, and sometimes we have a choice, sometimes we don't, so we can place them vertically and horizontally. And now towards the end you see we run into a problem and we cannot completely tile the board. So now there are 2 possibilities. First, maybe we made a mistake. We should go back and do something different. Or it could be that it's simply impossible to cover the whole chessboard with domino tiles. Okay, how do we find this out? Well, we live in the age of computers. We could program a computer to try all possibilities and simply exhaustively search for a perfect tiling, or tell us that the computer didn't find any. All right. So if we do that, maybe it's a wise thing to think about how long the computer would take to compute this. I mean, computers are fast, but still, their speed is finite. So how many possibilities would the computer have to check? Well, this is kind of difficult to compute. Let's take some close approximation. Let's put the 2 corners back in, and let's ask ourselves how many different ways are there to tile the complete chessboard. And this is maybe a good approximation to how many things our computer program would have to try out to find a tiling. Okay, so this is actually already a great example of discrete math. You have a fairly simple problem, you have a fairly simple question: how many ways are there to tile the chessboard using these domino stones? And these questions can become very difficult pretty quickly. So this question, for example, we will not solve in the course. We'll solve easier ones. Anyway, for now, let's cheat a little bit and let's go online and check Wikipedia. So Wikipedia has a page about domino tilings. This is exactly what we want, and thankfully it also has a link to a great website which is called the Online Encyclopedia of Integer Sequences. So whenever you run over a sequence of natural numbers you think it might have some significance, it is probably in this encyclopedia, and it tells you what it is about. So here we look at it, and now we can find out the number of tilings of our 8 times 8 chessboard. It is roughly 13 million. All right, 13 million is a large number. It's certainly too large for us to check all these possibilities. But for a computer it should be kind of okay. For a fast computer it should be okay. But then again, we are mathematicians. We are not only interested in 8 times 8, we are interested in the problem in its generality. We want to understand it. So even if the computer can't solve this problem, what about a bigger chessboard, 16 times 16? Can the computer iterate through all possibilities here? Well, again, let's go to the online dictionary of integer sequences, and there we also find the number for 16 times 16. And it is this. That's a huge number. It's so huge, I don't even know how to say this number in English. There is a better way to get a feeling how huge this number is. So suppose our computer needs 1 second to go through all combinations, to go through all tilings of the 8 times 8 chessboard. 1 second. How long would the same computer program need to go through all tilings of 16 times 16? Many. Actually take 400,000 times the age of the universe. So you see here, even with very fast computers, this approach of just letting the computer try everything is completely hopeless. So let's not do it. There is only one way that is viable. We have to start thinking. So often in math, if you're faced with a problem, it's smart to put additional structure to it. So for example, here we have this chessboard. And as the name actually suggests, if it's a chessboard, we should color it in black and white. So now we have 32 black squares and 30 white squares. And now what happens if we put a tile here? Well, the tile covers exactly one white square and a black square, no matter where we put it. So after we have put one tile, we have that many black and white squares. And we go on, and in the end, we have 2 black squares left and no white square. So it means whatever we do, we always get stuck because there will always be 2 more black squares than white squares. All right, so now it should be obvious to you, basically obvious to everybody, that this is an explanation why we cannot tile this chopped off chessboard. And this little riddle illustrates something that's very important in math, and in discrete math in particular, and that's the notion of a proof. The notion of a proof is central to mathematics. And it's also the whole fun of mathematics. Math without proof is simply boring. So what is a proof? If you go to a lexicon, you look up the definition of a proof, you will probably see something like a proof is a sequence of mathematical statements where each statement follows from the preceding ones by some agreed upon logical rule. Well, that's kind of true, but in real life a proof is something more. A proof is a formal explanation why something is true. Just as I told you here with the black-white coloring, it's an explanation that makes it completely clear why this holds, why you cannot tile the chessboard. So maybe you have got a little bit feeling how discrete math feels and what it's differs from other parts of mathematics, and I want to elaborate on this a little bit. So here are 4 areas of mathematics, and many of them were actually motivated by applications from outside math. For example, geometry is one of the oldest parts of mathematics. It's roughly 2,000 years, maybe 2,000 or 3,000 years old. And why did people start studying math? So here, for example, you see a page from a Chinese book from roughly 3rd century. And as you can see, they probably used geometry to measure distances on land. They wanted to measure their land, they wanted to measure areas of their plots. They needed geometry to build houses. You probably cannot build the pyramids without some knowledge of geometry. How about calculus? This is a much younger subject. So calculus, you remember from high school, it's about functions with real numbers, it's about derivatives, it's integrals. And it really got going in the 17th, 18th century with Newton and Leibniz. And also they started to study calculus because of some applications. So in the case of Newton, he developed calculus because he wanted to understand how objects, physical objects, move. First and foremost, for example, the planets, how the planets move around the sun. And for this, in order to understand this, he needed to develop this new area of mathematics. So also here, it came from a concrete application. Number theory is a little bit different. It is one of the oldest parts of math, but for 2,000 years it was basically just a beautiful game. A very beautiful one, but without any application. Until in the 70s, 2 mathematicians, Diffie and Hellman, used some number theoretic concepts to start something that is called public key cryptography. So here on the right-hand side, you see a scheme how 2 partners, Alice and Bob, can agree upon a common secret, a shared key, without ever meeting in private. And to understand how this works, you need to understand some basic number theory, you need to understand prime numbers, and so on. So since then, number theory has found a lot of applications, mostly in cryptography. Finally, discrete math. Discrete math really got going in the second half of the 20th century, and the technology that motivated people to study it was, of course, the computer. And why is this? Well, if you think about how the Earth revolves around the sun, it's a continuous motion. That's why we need calculus. On the other hand, computers are not continuous. They move in discrete steps. They do a step and a second step and a third step. So to understand how computers process information, how information is structured, you need discrete math. And this is why discrete math became big since the second half of the 20th century. All right, so I want to conclude this session with yet another example from discrete math. It is actually something that we will talk about towards the end of this course. It's called network connectivity. This is one of the most beautiful, in my opinion, one of the most beautiful results in discrete and basic discrete math in this course. So you have a network, here you see a network. You have a start vertex and a target vertex. And this represents something. It could, for example, represent a computer network where you want to route data from the start vertex to the target vertex. It could symbolize a rail network where you want to route train traffic. It could be a pipeline network where you want to route oil from the well, from the well to the refinery. But you know, which resource you want to route actually does not matter. So let's, abstract from this and just consider this network. So for example, here I can route goods along the red path, the blue path, and the green path. All right. So note that this node here, we use it twice actually. But that's fine. We just must make sure that every link is used at most once, because the links have, a limited capacity. So here you see you can route 3 units of goods, whatever you want to route, from the start to the target. This is what I define to be the capacity of a network. It's the maximum number of paths you can find from S to T that don't share any link. Now put yourself in the shoes of a bad guy, maybe of a guerrilla warrior, of a terrorist, I don't know, an adversary who wants to destroy the network. So now suppose we want to disconnect the start from the target. What we could do, we could place 4 bombs at these crucial links. And if we blow up these links, the network is disconnected. That's what I call the vulnerability. It's the minimum number of edges you have to remove in order to disconnect the start from the target. And if you look at it, it's pretty clear that the capacity is at most the vulnerability, because every path has to pass through one of these crucial edges. But now look at this example. We can actually move the green path up here, and we make space for another path, an orange path. And now we see actually that the capacity and the vulnerability both are 4 for this network. And this is no coincidence. There is actually a theorem we're going to prove towards the end of this course. It's called the Max-Flow-Mincuck theorem. It tells you this identity holds in every network. So this is the first session. We have to talk a little bit about the practicalities of this course. As you might have noticed, it's a video course. So this means you can take advantage of the fact that you have video lectures. You can hit pause whenever you want. If I'm going too fast, you can rewind to listen again. If I'm going to prove something, you should hit pause. You should try to think about yourself. You should try to solve it. Maybe you succeed, maybe you fail, it doesn't matter. Then you can go back, and then we are going to do the proof together. We also have a textbook, which is this, an invitation to discrete mathematics. We roughly follow this textbook in this course. But always discrete mathematics, it's a little bit an arbitrary choice of topics because it's such a big field, and there is no clear order in which one should talk about these fields. So there are several textbooks, and I can, for now, recommend these 2. We'll also provide links on our webpage, so I highly recommend you to buy at least one of them. And finally, there are exercises. The exercises are really important. In my experience, you cannot do math, you cannot learn math without doing it. So really do it yourself, look at the exercises, try to solve them, do some hard work, invest time in them. It's really helpful. That's basically it for today. As a little goodbye present, I want to give you yet another riddle. That's one of my favorites. In this riddle, we have 4 coins on a table, and we can move them around. We can take this coin, Oh, by the way, this coin is, I think I have one here. This is the 1 yuan coin. That's the basic unit of currency in China. So you can take a coin, you can jump over another coin. Then, for example, you can take this coin and jump over this, and you land here. You can also take coins that are a little bit further apart, like this, and you land back here. So you can just take a coin, jump over another coin, and you land behind it on the same line at the same distance, but behind it. And now the question is, can you take these 4 coins in a small square at the beginning? Can you move around such that you end up at some point in a larger square? So try to solve this riddle. If it's too difficult for you, try the same with 3 coins. So they are in equilateral triangle. Can you make the equilateral triangle bigger? If this is still too difficult for you, try with 2 coins. All right, good luck, have fun with this riddle, and I see you next time. Thanks. So if you have 2 sets, you often want to talk about a certain relation that holds between the elements of these sets. Cartesian products are important because they allow you to talk about relations that the elements of 2 different sets might have. For example, here we have 3 fruits and 3 people, and we might want to ask who likes what. The answer could look like this. Alice only likes the kiwi, Bob likes the orange and the apple, and so on. Mathematically, what this relation is, it's a subset of the Cartesian product, right? So this, a subset, is called a relation. Actually, because here we are only talking about 2 sets, it's called a binary relation. If you know the game Cluedo, for example, you want to find out who killed whom with which weapon in which room. And an answer to this would be a relation, a 4-array relation. So for example, is A is the set of murder of potential suspects, B is the set of murder victims, C is the set of murder weapons, and D is the set of crime scenes, then R, a subset of this set, describes who killed whom using what at which location. Right? This would be a 4-array relation. Of course, in real life and also in mathematics, we don't use the set theoretic notation. We often just say Alice likes kiwis. This is, of course. And if you have a binary relation, you can easily depict it by just drawing an edge from an element to the other in which, if it is in this relationship. All right, there are actually some relations you have already seen in mathematics. So for example, A is smaller than B. So for example, 2 is smaller than 3. You could define it as a subset of pairs of, let's say, natural numbers. And A is less than B if there exists an x in the natural numbers such that A plus x equals B. You also might have seen this notation. It's called A divides B. And you could define it as the set of all pairs of integers such that there exists an x, an integer, such that A times x equals B. So all these you can think of as relations, subsets of Cartesian products. One of the most important concepts are functions. What is a function? Well, in calculus, I guess, you have seen stuff like this. F of x is x squared, or f of x is e to the x. So these are functions, obviously. But let's try to be a little bit more formal. So a function has a set A where it takes as input and it outputs elements in B. You can think of it as an input-output machine. And like these two functions we can write down explicitly, but often if we're talking about less standard functions, we have to define them in kind of a more involved way. So here is an example. If you have a set A and some fixed element little a in it, I define a function from the power set into the power set. Do the following: if you give me a subset of A, I check whether it contains the element A, and if it does, I remove it, and if it doesn't, then I add it to it. So this is a function from 2 to the A to 2 to the A. So actually the functions we'll encounter in discrete mathematics often look much more like this than something like e to the x or x squared. But these are also functions. All right. Actually, you can think about functions as being a special relation. For example, suppose there are these three fruits, and now all of them have been eaten. Now we can ask who has eaten the kiwi and so on, and the answer would be something like this. So every item has been eaten by exactly one person. And you see again, this is a subset of the Cartesian product. It's a function, but it's a special function. What makes it special is that for every A, there exists exactly one B, such that AB is in the relation. And this special relation we call a function. A function can have certain properties that are important, so I want to quickly introduce them. Injective means if you have A to B, so suppose you have a function A, f from A to B. Injective means the two elements can never collide. So if you have two different inputs, they must give a different output. Surjective means that you reach every element in B. So formally, for every B, there exists an A such that f of A equals B. And bijective just means injective plus surjective. And these concepts are important for the following reason. If A and B are finite sets, and you have an injective function from A to B, it should be pretty clear that A cannot be larger than B. If it's surjective, if you reach every element in B, it's clear that A must be at least as large as B. And finally, if they're bijective, it means that they have the same size. Actually, some people take the existence of a bijection as the definition of what it means to have the same size. All right, so here let's go back to our example, which is a function from 2 to the A times 2 to the A. It is actually a bijection. You should invest some minutes to figure this out. It's a bijection from a set to itself. Now I use the set builder notation to build the set E and the set O. E is the set of even subsets of A, and O is the set of odd subsets of A. And actually, now you see that F, if you feed it an element of E, it outputs an element of O. So you can think of F also as a function from E to O. And it's also kind of easy to see that it's bijective. And therefore, E equals O. So there are as many odd subsets as there are even subsets, right? And we prove it by giving a bijection. So we have proved something that is maybe not completely obvious. The last thing for today, I want to show you some beautiful result from set theory. This is not a course about set theory, but I think this is remarkable and it's also easy, so I should talk about it a little bit. The surprising fact is n times n has the same size as n. So recall, if you have two finite sets, then A times B is A times B, which means that, for example, A times A is A squared, which is larger than A if A has at least two elements. But now n has infinitely many elements, and here there is a paradoxical, surprising fact. Actually, n times n has the same size as n. And here is the proof. Actually, what does it mean to have the same size? Well, I will show you that there is a bijection between these two sets. So here are the natural numbers, and here are the natural numbers. So their Cartesian product looks like this infinite grid. And I will show you a bijective function from n times n into n by this. 1, 2, 3. So next to each element of n squared, I write to which number in n I want to map it. So I go like this, and you see no number appears twice, and I will reach all numbers. So this is a bijective function, and therefore, in this sense, they actually do have the same size, although this set appears to be much bigger than this. All right, that's actually as far as we go into set theory. From now on, we'll stay strictly within discrete math. All right, that's it for today. Thanks. Hello everybody, welcome to our third session. Last time we introduced basic mathematical concepts, especially relations. Today I want to talk about a special type of relation that's called an ordering. You have seen orderings before. For example, on the natural numbers, you've seen the ordering less or equal. Or on the integers, you have seen the ordering of divisibility. So these are orderings, and they play an important role in discrete mathematics, but they don't only exist in natural numbers and integers. Let me actually give you a completely arbitrary example of an ordering. We want to compare apples and oranges, although people tell us that you cannot do this. So these two fruits, there are actually, a lot of things we could compare. We could compare the taste, the price, the vitamin A content, vitamin B content, vitamin C content, and so on. So there are lots of parameters we could compare. For today, let's actually focus on two parameters. The first is the vitamin C content. The other is the iron content. So here we see this is the vitamin C and the iron content of apples and oranges, and to spice things up, let's add some other food items. So how can we represent this data nicely? Well, let's make a two-dimensional chart and let's put our food items into this chart. So now I want to define an ordering. I want to say A is less or equal than B if it contains at most as much vitamin C as B does, and at most as much iron as B does. Okay, so that's my ordering. Let's see how it looks like here. So for example, clearly the apple is smaller than the broccoli, it's smaller than the kiwi. The orange is also smaller than the broccoli, and both are smaller than the chili. The apple is also smaller than the spinach. But apples and oranges are incomparable because the orange is richer in vitamin C, but the apple is a little bit richer in iron. So they are actually incomparable in this ordering. And to make it complete, we would also have to insert an arc from the apple to the chili and from the orange to the chili, because also the orange is smaller than the chili in this ordering. Okay, this is an example of an ordering. Now it deserves a formal mathematical definition. Okay, are you ready for it? Let's go. So you have a set, you have a relation on it. So for example, we could depict the relation by these little arrows. Let's say this just means A, B is in the relation and so on. And a relation can have certain properties. So for example, we say R is reflexive if x is in the relation for all x. So here it basically means we have these little self-loops around each vertex. Second, we say R is transitive if, let's say you have xy and yz appears in your relation, then you always have xz in the relation. So let's draw a picture. If you have x arrow y and y arrow z, then this implies x arrow z. This is transitive. And R is antisymmetric if, well, this is a little bit counterintuitive, if x cannot be smaller than y and simultaneously y smaller than x unless they are the same. So basically it means you don't have such a thing. Okay, so now it works. Okay, great. So something like this doesn't happen. This means antisymmetric. So let's quickly summarize it. A relation that is reflexive, transitive, and antisymmetric, that's called an ordering. So now you can go back and check that these three properties actually hold for the less or equal relation on natural numbers, for the divisibility ordering on integers, and for our vitamin C and iron ordering on fruits. Some relations have the following bonus property. So for example, consider the natural numbers together with a less or equal. You always have A less or equal B or B less or equal A. Consider the divisibility. Well, divisibility we should actually write integers, not natural numbers. It could be that A does not divide B and B does not divide A. So this is possible. So it seems here that the less or equal relation has a bonus property. It means if you have two elements, you can always compare them. But the divisibility ordering doesn't have this. For example, 3 doesn't divide 7 and 7 doesn't divide 3. So this bonus property is called linear. It's called a linear ordering, sometimes also a total ordering. Just keep in mind, some orderings have this property, some don't. Okay? If it doesn't, then we call it a partial ordering. All right, so here is a summary. Reflexive, transitive, antisymmetric, that's an ordering. If in addition it's linear, it's a linear ordering. Cool. So let's look again at our ordering on food items. Let's look at this arc from the apple to the chili. It's actually redundant because even without the arc, we would know that the chili is larger than the apple by transitivity, right? You can just go from the apple to the broccoli and then up. So this arc is actually redundant. We can remove it, and the same with this arc. And now we are left with the non-redundant arcs. And this has a name. This is called the Hasse diagram of an ordering. Again, this deserves a formal definition. We call x an immediate predecessor of y if x is smaller than y and there is nothing in between. So you cannot find anything that is strictly between x and y. So for example, the kiwi and the chili are immediate predecessors, but the apple is not an immediate predecessor of the chili because the kiwi is in between. The broccoli is in between too. Okay, so now if for every immediate predecessor you include an arrow xy, then what you get is the Hasse diagram. And there is actually a cute lemma. If you have an ordering and S is a finite set, then the Hasse diagram uniquely defines your ordering. So if I show you the Hasse diagram, you can reconstruct the ordering. Now this condition S to be finite is actually crucial. For infinite sets, this lemma might be false. For example, consider the set 0, 1, the real interval, together with a smaller equal relation. So what is the Hasse diagram of this ordering? Think about it. Okay. We need some further important definitions concerning orderings. So first of all, if x is less or equal than y, or vice versa, then they are comparable. Otherwise, they're incomparable. And if you have an ordered set and you have a subset and everything in C is mutually comparable, like A and B are comparable for all A, B in C, then we call C a chain. Like it's a subset that is linearly ordered. And if you have the opposite, if any elements, all elements are pairwise incomparable, then A is called an anti-chain. So it's a subset where nothing is comparable. All right. This is chains and anti-chains. Now, an element is maximal if nothing is larger. If there exists no y in S that is larger. And it's called minimal if there exists nothing that is smaller. In general, this is different from the following definition. X is a maximum. It's a maximum if it is bigger than everything else. And it's called a minimum. It's called minimum if X is smaller than everything else. So just be aware that these two definitions are not the same in general. If your order is not linear, these might not be the same. Here is a summary where everything is nicely written. And here is an exercise for you. You should find the largest chain, largest anti-chain, maximum, minimum elements, and minimal and maximal elements in our food item ordering. One last thing, then we are done for today. Here we have an ordering S in this. And now suppose I'm only interested in this subset, X. Then my ordering induces a suborder, right? I just take the ordering, I restrict it to X, and I get a new ordered set. So every subset of S also inherits the ordering. This is called the induced suborder. All right, that's it for today. Here are some nice exercises. Those without star are quite simple. You should be able to solve them if you have understood the material of today. Those with 2 stars actually requires some non-trivial proof. So here is the first set, and here are some more exercises. All right, thank you for today. See you next time. Hello, Welcome to our video course on discrete mathematics. The topic of today will again be orderings, and in this lecture we will actually prove a non-trivial theorem and also see an interesting application. So as a quick review, what we see here is an ordering on a finite set. To be more precise, it's the Hasse diagram of this ordering, which we defined last week. We have also seen two important concepts, namely chains and anti-chains. So for example, this is a chain. It's a set of pairwise comparable vertices. And actually what I draw here is a chain of maximum size. So this is what I want to define to be the height of our ordered set. It's the size of the largest chain. Similarly, I define the width to be the size of the largest anti-chain. So in this example, the anti-chains are not very exciting. So you can see every anti-chain has size at most 2. So here the width is 2 and the height is actually 1, 2, 3, 4, 5, 6. It's 6. Let's look at another example. Here again we have an ordered set. The largest chain should be something like this. So the height here is 3. And the width is a little bit larger. So the largest anti-chain should be this in the middle. 4, 5, 6, 7, 8. So the width of S is 8. All right, so this defines the height and the width of an ordering. And now we are ready for the theorem of today, which is called Mirsky's theorem. It tells you the height of S is the minimum T that you can partition your set into T anti-chains. So as a picture, it basically means this is your set S. You somehow partition it into anti-chains. And somehow if you manage, this now is 1, 2, 3, 4, 5, 6. If you manage to partition it into 6 anti-chains, then no chain will be larger than 6. And actually these two numbers meet. So you can find a chain of some size and an anti-chain covering of the same size. So the proof consists of two parts. First, let's do the simpler half. Let's prove that the height is at most T. So let's take an anti-chain partition. This is A2, A1, A2. This is AT, and so on. And we have seen in last lecture that if we have a chain and an anti-chain, they can intersect in at most one element. Right? So if you have a chain, it can have at most one element in each of these levels. And therefore, it's immediate that you cannot have more than T elements in the chain. So this proves the upper bound. So this was easy. For the lower bound, namely that the height is at least T, we must do the following. We must find a partition of S into anti-chains, and we must find a chain T, a chain C, of size at least T. So this is what we have to do to prove the lower bound. And how are we going to prove that? Well, it's actually not that difficult. Let's draw our set S. So this is S. And here is a kind of obvious choice for an anti-chain partition. We start with the minimal elements. So A1 is the minimal elements of S. And as we have seen last week, this forms, in fact, an anti-chain. So now what is A2? Well, A2 is the minimal elements of whatever is left. So formally, A2 is the minimal elements of S minus A1. So we can work our way up. Let's say this is AI. How do we define AI plus 1? AI plus 1 is the minimal elements of S when I remove everything below it. So I remove the elements A1 until AI, and whatever is left, I take the minimal elements of this, and this is A1. So in every step, we remove at least one element, and therefore this process terminates with a set AT. Good. So this is our anti-chain partition. So now what we have to do, we have to find a chain that actually has T elements. So here is the lemma. For all elements X in anti-chain AI plus 1, so let's say X is here, there exists an element Y one level below such that X is smaller, no, the other way around, such that Y is smaller than X. So something like this. The proof is very simple. Well, if none such Y existed, so otherwise X would already be minimal in the set S minus A1 up to AI minus 1, and we would put X into AI and not into AI plus 1. So this is a contradiction, and therefore we can be sure we find some element that is smaller than Y. Right, and this almost finishes the proof, because now we can take any element in AT, we find an element smaller in AT minus 1, and so on until we are down here. Right? And this is your chain of size T. And that concludes the proof. So now again, let's look a little bit more in depth at Mirsky's theorem. Here is one way to state it. The maximum size of a chain is the minimum size of an anti-chain partition. And a theorem of this kind, where you say the max of something equals the min of something, is called a min-max theorem. So every time you discover a min-max theorem, you should rejoice, because these are kind of the highlights of discrete mathematics. We'll see in the course of this lecture, we'll see many more min-max theorems. Here's another way to formulate Mirsky's theorem. In a more logical way, you can say S can be partitioned into T anti-chains if and only if every chain has size at most T. So note that the only if part is very easy, and the if part required a little bit more work. So we can say the obvious necessary condition is also sufficient. And this provides a nice nickname for theorems like this, TONCAS. This is just an acronym. The obvious necessary condition is also sufficient. The Mirsky theorem is an example of a TONCAS. Another thing, on the left side here, we have chains, and on the right side we have anti-chain partitions. So now what happens if you switch these two terms? You ask yourself, is the max size of an anti-chain equal to the minimum size of a chain partition? Is this statement still true? And it turns out, yes, it is still true. It has another name. It's called Dilworth theorem. Today we can prove 1/2 of Dilworth theorem, which is this inequality. So if you have an anti-chain in a chain partition, your anti-chain must be smaller, must be at least at most the size of the chain partition. So the proof is very similar to the first half of Mirsky's theorem. If this is your set S, and you have a chain partition, something like this. This is C1, then here's your chain C2, this is C3, C4, and so on. And you have an anti-chain, A, then we also know A intersect Ci is at most 1. So again, our anti-chain can have at most one element in each chain, and therefore A is at most T. So this proves the first half of Dilworth's theorem. Now the other half, for the other half we would have to find a chain partition and a large anti-chain that match in size. And this is actually much more difficult, and it requires some tools that we do not yet have. So we have to wait a couple of weeks. But I promise you, when we come to the topic of matchings in bipartite graphs, then we have the tools to prove Dilworth's theorem. But for today, we have actually to put up with just proving 1/2 of it. All right, So here is an application of Mirsky's theorem, a direct corollary. It tells you if you have a set S, then one of the width or the height must be large. So the product of both must be at least S. Why is that? So why is that? Well, you see, there must exist an I such that AI is at least S divided by T. Right? Because all sets together make up whole of S. And what is this? By Mirsky's theorem, this is S divided by the height. This proves the theorem. All right. Here is a nice application. So what you see here is a sequence of integers. 1, 3, 2, and so on. So what I mark here are integers that are increasing. So this is an increasing subsequence. And there are also decreasing subsequences. For example, this is a decreasing subsequence. And now there is a famous theorem by Erdős and Szekeres. It says if you have n distinct integers, then either you find a long increasing subsequence, long meaning at least square root n, or a decreasing subsequence of length at least n, square root n, or both. But you find at least one of the two. So how can we prove it? Well, actually, it follows pretty directly from Mirsky's theorem by the following proof. So we take a sequence of numbers and we put it into a two-dimensional space. So note the first element in my sequence is 1, so I should put it down here. The second is 3, so I should put a vertex here. The third I put here. And the fourth is 8, so I should put it somewhere up here, right? So I can take my sequence of integers and I get a set of points in n square. So now we know that n square with this relation is a partially ordered set. And this is the Hasse diagram of this partially ordered set. And the key observation is if you have a chain in this partial ordering, then this corresponds to an increasing subsequence. So this is 1, 2, 4, and 13. This is an increasing subsequence. And similarly, if you have an anti-chain like this, it corresponds to a decreasing subsequence. So in this case, this would be 8 and 7. And now you see that the largest increasing subsequence, the size of the largest increasing subsequence is actually the height of our partial ordering, and the size of the largest decreasing subsequence is the width. And therefore, the product of these two must be at least n by Mirsky's theorem. So one of them is at least square root n. So here's a summary. Here you can see the Erdős-Szekeres theorem that we have just proved. Actually, you can state it in a little bit more general form. If you want, you can easily verify that the same proof that we gave also proves this more general form. All right, that's it for today. Thank you for listening, and I see you next week. Goodbye. Hello everybody, welcome to our video lecture on discrete mathematics. A big part of discrete mathematics is actually counting all kinds of things, all kinds of mathematical objects. And in today's lecture, I want to start with this topic, which is called enumerative combinatorics. And we start with counting the basic mathematical objects we have defined in the last lectures, like sets, functions, and so on. So as a motivating example, suppose I have to plan which dinner to cook for the next 3 days, Saturday, Sunday, and Monday. And let's suppose my cooking abilities are a little bit limited, and these are the 5 dishes I can cook. I can cook Chinese food, Mexican food, German food, pizza, and pasta. So, for example, something I could do is I could say, well, on Saturday I cook Mexican food, on Sunday I could cook German food, and on Monday I didn't make a pizza. Okay? That's a perfectly fine thing. What I could do, well, I could also be lazy and say, well, on Saturday I make pasta. On Sunday I make pasta. And on Monday I make pasta. Now that's probably a boring dinner plan, but for now this is actually allowed. So I have no restrictions, I just have to cook 1 dinner per evening. So now the question is, how many choices do we have? How many choices do I have to cook dinner for the next 3 days? And this is very easy. So on Saturday I have 5 choices, on Sunday I have 5 choices, and on Monday as well. If I multiply them together, I have 125 choices. All right, so what you basically just have proved is the following fact: the number of functions from the set Saturday, Sunday, Monday into the set Mexican, German, Chinese, pizza, pasta is 5 to the third, which is 125. And in general, if you have 2 sets, A, B, the number of functions from A to B is B to the A. So here's an application of this innocent fact. So you might remember we have defined the power set of a set 2 to the s to be the set of all subsets. And now we're asked the following question: how many subsets are there? So for example, this is a subset. This is also a subset. But the set itself is also a subset of itself. And of course, the empty set is also a subset. So how can you count the number of functions? Here is a little trick. For a subset, I define 1 sub x. This is the characteristic function. It's a function from S into the set 0, 1, defined as follows. 1 sub x of A is simply 1 if A is in the set X and it's 0 otherwise. And now you actually see that there is a one-to-one correspondence between characteristic functions and subsets. And therefore, we see, well, the number of subsets, the size of the power set, is simply the number of functions from S into 0, 1. And by what we have just proved, we see that is 2 to the size of S. All right, so here's the proof again, written up in a nice way. You can look at it in more detail if you wish. Let's continue to part 2, counting injective functions. So, as I have told you, there are no restrictions to cooking food for the next 3 days, but of course, maybe my wife is not happy with me cooking Mexican food twice, so she actually wants that I cook 3 different dishes over the next 3 days. So this is not good. What would be good, for example, would be something like this. Just now the rule is no food twice. So basically now we are looking for an injective function. So how many choices do we have now? Well, for Saturday I still have 5 choices, and no matter what I chose, I have 4 choices left for Sunday and 3 choices left for Monday, and together this gives 60. In mathematical terms, it means the number of injective functions. That's actually a typo here. It's not infective, it's injective. Okay, the number of injective functions from Saturday, Sunday, Monday into my 5-element set is just 5 times 4 times 3, which is 60. And in general, if you have 2 finite sets A and B, then the number of injective functions is this expression here. And this is so important that I want to introduce a notation for this. This is very useful, but it's not completely standard in mathematics. So b to the a with a little line under it, it's just defined to be b times b minus 1, b minus 2, and you continue until you get a factors. And this is pronounced b to the falling a. All right. So get used to this notation. It's actually quite useful in enumerative combinatorics. So we have proved the number of injective functions from a to b is b to the following a. All right, so in part 3 I want to count permutations. What's a permutation? So let's change the setup a little bit. I'm planning a 5-course dinner for one evening. So there is one evening and I want to cook all the food that I can cook. So there are these 5 choices, so I have to cook everything. But I'm not sure in which order I should serve. So for example, I could say the first course is Chinese, the second is German, and so on. Or I could choose a different order, or this, and so on. And actually, as you already see, there are lots of combinations I can do. There are lots of ways in which I can order this 5-element set. How many are there? So here's the thing. The only thing I have to decide is what is the first course, the second course, the third, the fourth, and the fifth. So basically what I have to do, I have to choose an injective function from this set into the set CG M pasta pizza. Right? And how many such functions are there? Well, 5 to the following 5, which is 5 times 4, 3, 2, 1, which is 120. So we've proved the following theorem. These elements can be ordered in 120 different ways. And in general, if you have a set of size n, then it can be ordered in that many ways. And this is also a very important formula in mathematics. So we again introduce a new notation. And we pronounce it n factorial. Okay, and if you haven't discovered it yet, I have discovered a typo. This is of course supposed to be n minus 2. All right, another thing to observe, the n factorial is simply the number of functions from a set, the number of injective functions from S to itself. And if such a function is injective and S is finite, then this function must be bijective. And a bijective function from a set to itself we also call a permutation. All right, so we are ready for the last part of today's lecture, counting subsets of a certain size. So the setup is here. I'm invited to a party and I have to bring 3 dishes. So I just have to select 3 of the dishes I can cook. So for example, these here, okay, or these 3, and so on. All right, so how many are there? Well, one way to solve it is again to say, well, I have the set 1, 2, 3. I have to select the first, the second, and the third dish to bring. So I have to find an injective function from this set into this set. For example, this. So now we could say, well, you know, the number of choices is maybe 5 to the following 3, because this is the number of functions from the left set into the right set. But now you might protest and say, well, it's not completely true, because if I draw this function, it's a different function, but it gives me the same set, like this, right? It's a different function, but it gives me the same set. So every set can be obtained by a lot of functions. By how many? Well, if you think about it, by 3 factorial many. So what is this? This is 5 times 4 times 3 divided by 3 times 2 times 1. This is 10. So I have 10 possibilities of selecting 3 dishes. So this is the following observation, and in general, if you have a finite set, then it has this many subsets of size k. And this is also very important, so I want to introduce a little bit of notation. So the first thing is S choose k. This is just the number, it's the set of subsets of S such that x has size exactly k. And then this expression here we pronounce it n choose k. We pronounce this S choose k. So we basically have proved that the size of S choose k is the size of S choose k. And this thing is very important. It has its own name. It's called a binomial coefficient. The binomial coefficient is arguably maybe the most important object in enumerative combinatorics, so we will see it a lot during the coming sections. All right, that's it for today. Thank you very much and see you next time. Hello everybody. Last session we started with the topic of enumerative combinatorics, and I showed you how to count basic mathematical objects like functions and subsets. Today, in the next couple of sessions, we'll continue with more sophisticated ways of counting things. As an example, let's play with blocks. So let's take blocks and build a pyramid like this. Okay, it's not a very sophisticated pyramid anyway. So the question I'm asking now, how many blocks do we need to get to a certain height, for example 6? I mean, of course, we can just, add up 1, 3, 5, 7, 9, 11 and calculate it. But of course, I mean, our goal is to derive a formula that lets us do that in a compact fashion. And here is a very nice geometric way to derive a compact formula for this. Let me take this pyramid and let me split off the left half. It's actually a little bit less than the half, but whatever. So we split off the left part of the pyramid, and now we rotate it. And now you see it fits in perfectly, and it gives us a square of side length 6. So of course we see the number of blocks here is 36. So you can do that for any height, and this actually is a kind of a geometric proof that the first n odd numbers sum up to n squared. All right, now let's actually not play with blocks, let's play with bricks. So if we build a pyramid with bricks, of course, what we are doing, we're going to shift the next layer. So the two layers are not aligned, but they are shifted. This is kind of a more efficient way to build a pyramid. And now if we want to go all the way up to height 6, how many blocks, how many bricks do we need here? In other words, what is the sum 1, 2, 3, 4, 5, 6? And again, here is a geometric trick how to compute that, how to get a formula for this. It's a little bit more sophisticated. So what I have to do, I have to actually double the pyramid. So now I have these two pyramids, and I rotate the yellow one. Well, I rotate it, and now it fits, and it builds this. It's not a rectangle, it's a parallelogram. Anyway, now we see that every row has 7 bricks. Yes, 7 bricks, and there are 6 of them. So it should be 42, right? So one pyramid would be 21. And this, of course, can be generalized to every natural number n. The theorem is the first n natural numbers sum up to n plus n times n plus 1 over 2. And there is a famous legend about the German mathematician Carl Friedrich Gauss. I mean, he's a brilliant mathematician, and already when he was in high school, he was kind of brilliant. So there is this anecdote that the high school teacher gave the class the exercise to just add up the first 100 natural numbers, something like this. Now, of course, this is not a very difficult exercise, but it's a very boring and time-consuming exercise, and maybe the teacher wasn't really well prepared and just, wanted to kill time. But Gauss as a mathematician, he didn't want to do all the work if there is a smarter way to do it. So what Gauss did, he observed if he takes the sum again, but reverses the order in which he adds it up. So he goes from 100 down to 1, and now he adds up term by term, then every term adds up to 101. And how many terms do we have? Well, we have 100 terms, right? So this should be 100 times 101, which is 10,100. And so the total sum should be half of that. So Gauss was finished after, let's say, 3 minutes, and whereas the teacher would have expected his students to take an hour or something. So the teacher was actually quite surprised. Cool. Okay. So these are the two things we have learned. So when I maybe was in junior high school, I'm not as brilliant as Gauss. So I got frustrated that I couldn't find a compact formula for this sum here. So instead of adding up the numbers, he added up the square numbers. And I tried a little bit, but I didn't seem to get anything meaningful. And of course, later I learned that there is a nice compact formula, but it's not as nice. So here's a kind of a geometric interpretation of this sum. Again, but we play with blocks, and we take this big square, we put in kind of the smaller square, and so on. So we get the three-dimensional pyramid. And now we're asking how many little cubes are in this big pyramid. And I don't know about you, but I don't see any nice geometric way how to break this pyramid apart and arrange it in a way that gives us a nice formula. I don't know. I don't see any geometric way. And how about this? So we add up the first n binomial coefficients, n choose 2. Geometrically, this corresponds to something like this, building something like a tetrahedron out of little ones. So we could take these 4 guys and build this tetrahedron, and now we're asking how many little dots are in this tetrahedron. And also here, I don't see a way to manipulate things geometrically to fit into a nice object. So the geometric interpretation helped us in the beginning, but now it maybe doesn't help us. And if you think about more complicated sums like this or like this, of course we don't have any geometric intuition anymore, because this would be like 4 or 5 dimensional space. So you see, this playing around with blocks was a nice way to illustrate the proof, but it doesn't carry us very far. So if we want to determine a nice formula for these kind of sums, what we need to do, we need to understand a lot about the coefficient, about the binomial coefficient. And this will actually be the topic of the next lecture or the next 2 lectures, trying to understand the binomial coefficient in order to evaluate these sums and count more complicated things. That's it for today. Thank you. Hello everybody. At the end of last time, we saw that we need a deeper understanding of the binomial coefficient n choose k if we want to obtain compact nice formulas for certain sums and count more sophisticated objects. So this time we start the battle against the binomial coefficient. Let's see how far we get. So the first thing I want to show you about the binomial coefficient, it satisfies this nice recurrence. So this fact actually has two proofs. One is just by pure calculation, and one is more by thinking about what n choose k means. So let me give you the proof by calculation first. So remember, we have a formula for the binomial coefficient, which is n factorial divided by k factorial times n minus k factorial. And now we can just plug in this formula into our recurrence up here and see whether it works out. So let's try to do that. So what is n minus 1 choose k plus n minus 1 choose k minus 1? Okay, let's just plug in the definition, the formula that we have. This is n minus 1 factorial divided by k factorial. And here we get n minus 1 minus k factorial. And here we get n minus 1 factorial. Then here we get k minus 1 factorial and n minus k factorial. Okay, let's put the fraction together. So what is the common denominator? The common denominator is k factorial n minus k factorial, which is already quite good. And the first term we have to multiply by, so this we have to multiply by the term that's basically missing down here. This would be, which term is missing down here? That is n minus k. And here in the right term, the factor that is missing down here is a factor of k. Okay, so this is times k. And now you see we can factor out the n minus 1 and get n minus k plus k divided by this. Now this is of course just n, and then this together gives you n factorial. So we are done, because this is again the formula for n choose k. But this is just a proof by pure calculation. It's not very inspiring. Let me show you a little bit more inspiring proof that actually tells you why this recurrent formula is true. So let this be our set of size n, and let's take an element x in the set. Now if we select a subset of size k, this is a subset x of size k, there are two possibilities. First, we include this element x in our set, and we select k minus 1 additional elements from the rest. And for this, how many choices do we have? Well, n minus 1 choose k minus 1, right? Because there are n minus 1 elements left, and we have to select k minus 1 from them. Or we could choose to not include x. But then we have to select k elements from the rest. I mean from the set without x. So for this, now we have n minus 1 elements left, and we have to select k of them. So the total number of choices is just this plus this. All right? So together, it gives the full number of choices, which we have seen as n choose k. Right? This is a more intuitive proof of the recurrence formula. So here's a nice thing, kind of a fun thing you can do with this formula. So let me write, for example, 3 choose 0, 3 choose 1, and so on in one row. What it basically tells you 4 choose 2 is simply the sum of these guys upstairs, and 4 to the 4, I mean, technically would be the sum of this, but what do we have here? Well, here technically we have 3 choose 4, but this is of course 0 because you cannot select 4 elements, right? There are not enough elements around. So you can get kind of this. And I mean, if you do that, so let's fill in the numbers. You see kind of the first row we have here is 1, 3, 3, 1, and then the next would be like this. And of course, I mean, this row also comes from something, so actually we can start like this. Like this would be 0 choose 0, and then this would be 1 choose 0, and so on. And we get the next row by just adding up the 2 neighbors upstairs, and it goes on like this, like 15, 20, 15, 6, 1. And let's do one more. Okay, my computer is bugging me about some whatever, you know, some Wi-Fi or something. No idea what. All right, so we get a kind of triangle where the nth row at the kth position has the binomial coefficient n choose k, and this has a name. It's called Pascal's triangle. And a fun thing happens if you take Pascal's triangle modulo 2. So you're only looking at which numbers are odd and which are even. So let's mark all the odd numbers. So these are odd, this is odd, and then this is odd, and here this is odd, this is odd, this is odd. So we get kind of a certain structure, and if you use a computer to plot this, or you simply go to Wikipedia and look at the figure, you get this kind of nice fractal-like object, which is called Sierpinski's triangle. So this is called Sierpinski triangle. So let me write, this is basically n choose k modulo 2. Another important thing with a binomial coefficient appears is the following formula. So in high school, you might have learned the following formula: x plus y squared is x squared plus 2xy plus y squared. And maybe you even remember the formula for this. Anyway, but today we'll see a formula for general n, which is the following. It's called the binomial theorem. X plus y to the n is this complicated looking sum. And let me explain it a little bit. So here, this is an expression with 2 variables. This is called a binomial, and this is its coefficient, right, in this expression. And therefore, it has the name binomial coefficient. So there it's actually where the name comes from. So again, I want to show you 2 proofs of the theorem. First, one with a lot of calculation, and then a proof with just thinking. So here's the first proof. We use induction on n. Our base case is that n equals 0, in which case x plus y to the 0 is 1. And the right-hand side would be this sum from 0 to 0, 0 choose k, x to the k, y to the 0 minus k. You can simply, you can easily check this is also 1. So for the step, we suppose the formula is correct for n, and we have to prove it for n plus 1. So what is x plus y to the n plus 1? Well, one thing that is easy to see, it's x plus y times x plus y to the n. Okay, so now by induction we can plug in the formula for x plus y to the n, because we can assume by induction that the binomial theorem is true. But here's a little trick to make things a little bit easier. So in this sum, we sum up from k equals 0 to n, but actually you can convince yourself we can actually sum up over all values k, over all integers k, Because if k is not in this range, for example, if k is negative or k is larger than 0, then n choose k is, if you look into the definition, anyway 0. So by just letting k run over all integers, we just add a bunch of zeros, so we don't change the sum. But it makes the proof a little bit easier. Okay. So we use the induction hypothesis and see that this is x plus y times the sum over all k, n choose k, x to the k and y to the k minus to the n minus k. Okay, now we can expand this product. We get x times the sum plus y to the sum, so we get now two sums. The first sum we multiply by x, so we get k plus 1 up here. And the second sum we multiply by y, so x to the k, y to the n plus 1 minus k. And now we do some little trick that's called a change of variable. We say, hey, look, in this sum, we rename k plus 1 to bj. And if we do that, then we get the sum over all j into the, now you have to think, what is k? Well, k is j minus 1. And now we get x to the j, y. And now you have to think, what is n minus k? Well, n minus k turns out to be n plus 1 minus j. And here we simply get the same sum. And now you see with this change of variable, because we set k ranges over the whole integers. Now if we set j to be k plus 1, it also ranges over the whole integers. So we don't need to keep track from where to where the variable runs. And this makes this change of variable a little bit easier. We just have to think less. And now you see this term here is the same as here. So now we can pull the two sums together and we actually get the sum over all k, x to the k, y to the n plus 1 minus k, times the sum of these two things, times, let's see whether I have enough space, n choose j minus 1 plus k minus 1 now, change the name back, n choose k, and by our recurrence formula, we know that this is simply n plus 1 choose k. All right, so this is an inductive proof of this theorem. Now that would be the last thing for today. I want to show you a kind of more intuitive proof of this theorem. So x plus y to the n equals, we can just write it out. And if you think about it, this is a sum of 2 to the n terms. Right? If you multiply it out, for every combination you get a summand, so you get 2 to the n in total. And when do we get like x to the k times y to the n minus k? Well, when we select x in k out of all n parentheses x plus y. And there are n choose k ways to select that. And therefore the coefficient of x to the k times y to the n minus k is exactly the binomial coefficient n choose k. All right, that's it for today. Thanks. Hello everybody! Today we continue our battle against the binomial coefficient, or to put it in less belligerent terms, we try to understand as much as possible about it. So I want to show you some surprising identities involving the binomial coefficient. So for example, what do you think? Can we find a nice expression for the sum? Yes, we can, but that's not the point. The point is I want to show you a method, an abstract method, how to come up with formulas for such more or less involved sums. So we have this formula. Our goal is to find a more compact expression for it. And the way we do that is we start by finding a combinatorial interpretation of what we have. And here's our combinatorial explanation. Suppose we have a parliament of size n, and within the parliament we want to select a committee. Now let's say the committee has size k, and the committee needs a speaker who is also a member in the committee. So how many choices do we have to do that? Well, you see, to choose the committee of size k, we have exactly n choose k choices, and once we have chosen the committee, we have k choices to select a speaker. Now, if I don't restrict the size of the committee and I can say, well, it can be whatever, it just must have a speaker, then in order to get the number of possibilities, I have to sum up over all values of k. So this is our interpretation of this sum. You have a parliament of size n, you select a committee, and once you have the committee, you select the speaker. All right, so now we can actually write that down in a more compact form by inverting our selection of committee and speaker. So again, we have a parliament of size n, but now what we do is we select the speaker first. So we have n choices to select the speaker, and once we have selected the speaker, we have to select the committee. And in order to select the committee, we have to decide for each member of parliament whether we put them into the committee or not. So we have two choices for each member of parliament, except for the speaker. For the speaker, we have only one choice. He or she must be in the committee. Okay, so we have n minus 1. We have to make n minus 1 choices, so the total number of combinations is 2 to the n minus 1 times n. All right, so you see how we derived an elegant formula for this unwieldy sum. Now let's see how far we can push this approach. Can we use it to compute a nice formula for this sum? So let's try again. Okay, let's try this. We have a parliament of size n. We select a committee, and the committee might have size k, so this is n choose k, and then, well, k squared. What is a combinatorial explanation for k squared? Well, we could say the committee needs a speaker and a chairman. And they could be the same person, so we have k squared choices. So that's a combinatorial interpretation of the sum. So to do it, let's again invert it. Let's say first we select chairman and speaker. So for this we have n squared choices, and then let's select the committee, but the committee must contain both the speaker and the chairman. So how many choices do we have? Well, we have a choice to include or not include each member of parliament except chairman and speaker. All right, so what we have just done is we have derived a wrong formula. You can easily check the formula that we have derived is wrong. Of course, where's the mistake? Well, here it could be that chairman is also the speaker. And in this case, we would have 2 to the n minus 1 choices, not n minus 2 choices, to form the rest of the committee. So now we have to make a case distinction. Is the chairman the same as the speaker or not? And then our formula gets less nice. So maybe we should dump the whole problem and start with a nicer problem. So let's take a nicer problem, this sum. Let's actually compare. In this sum you have k squared, and in this sum we have k choose 2. So there is again a nice interpretation. We have a parliament or committee, and now we just select 2 speakers. So of course the committee again has n choose k possibilities, and then we just select 2 members from the committee to act as speakers. So this is k choose 2. We can again invert this election process and can say this is our parliament. We first select the speakers. For this we have n choose 2 possibilities, and then these are really 2 people. So now we have to select plus n minus 2 others for the committee. Well, for the n minus 2 others, we have to make a choice whether to include them into committee or not. So we get the following formula, n choose 2 times 2 to the n minus 2. Alright, so for the binomial coefficient it was much easier to derive a formula because we don't have this stupid case distinction, because we say from the beginning that the 2 speakers must be 2 different people. Alright, so actually we can generalize this, and instead of, let's go back here, instead of this, oh my god, here I made a typo, let me correct this. This should be k and this should be a, right? Anyway, sorry about that. The way we do that, again we have a parliament, a committee, and now we select a speakers. Speakers. Yes, and this should be k choose a. Just by the same token we can invert it. First we select our set of speakers, which is n choose a, and then we select our committee of any size, for which we have 2 to the n minus a possibilities. Okay, so we saw a bunch of combinatorial identities and had an intuitive proof using some of these combinatorial interpretations. So let me actually show you another example, because this we will need later. So we have this sum here, which I can compactly write as this, and actually we can also start the summation at 0. It doesn't really make a difference, it's just adding a bunch of zeros, doesn't make a difference. Well, okay, how can we derive a formula for this? Well, this is a little bit tricky, but here is how you do that. Again, you take your parliament, but now you say it has size n plus 1. And you order your members of parliament from youngest to oldest. Okay, so now what is our combinatorial interpretation of the sum we have up there? Well, interpretation is as follows. We again select a committee, but now we say the chairman of the committee or the speaker of the committee must simply be the oldest member of the committee. So what we can do is we select a speaker, and then we select the rest of the committee. So here now we form a committee of size k plus 1. Okay, we have n plus 1 members of parliament and we want to form a committee of size k plus 1. The way we do it, we select a speaker S and then we select the k remaining members. So we say k more members but from which set? Well, they must be younger than the speaker. Because the speaker, our rule is the speaker is the oldest member of the committee. So here we have S minus 1 choose k choices. So in total, this would give us, we sum over all possibilities for the speaker, which is the sum from S to n plus 1. And now by a change of variable, this is simply summing up m from 0 to n, m choose k. So this is it. This is our combinatorial interpretation of the sum. So now how can we get a compact form? Well, just, by selecting the committee in a different way, in a different order. So here's another way. First, we select the k+1 members of the committee. So here we have n plus 1 choose k+1 choices. And second, we let the oldest committee member be the chair. So how many choices do we have for this? Well, simply one. Therefore, we see this sum sums up nicely to this. All right? Let's again write it up nicely. All right, and now please remember that we have the following formula for the binomial coefficient, m to the falling k divided by k factorial, where we defined m to the falling k to be m times m minus 1, and you continue like that until you get k factors, so m minus k plus 1. This is m to the falling k. So if you substitute this for m choose k, you get the following formula. You get m to the falling k, if you sum up from m equals 0 to n, you get n plus 1 to the falling k plus 1 divided by k plus 1. So if you have trouble memorizing the formula, here is kind of a little a little analogy that might make it easier. So if you for example take x to the k and you integrate from 0 to y, what do you get? Well, you get y to the k plus 1 divided by k plus 1, right? So the formula up here is like a discrete analog of integration. All right, so we have just derived this formula. Now let's see a simple application. You remember 2 sessions ago I told you I was frustrated as a high school student because I couldn't come up with a nice formula for the sum of k squared. So now we can. Because now we can simply observe that k squared, we can write it as this. That's actually kind of a stupid way to write it. Why should you write it? Well, because this is now 2 to the falling k, k to the falling 2 plus k to the falling 1. So we see we can actually pull out the sum into 2 sums. And now from what we have learned, this is k plus 1 to the falling 3 divided by 3. And here this is k plus 1 to the falling 2 divided by 2. So now, of course, you can put that together and you get a nice formula for it. So this is how you can actually derive a nice formula for the sum of k squared, and actually for k to the 4 and so on. You can try to kind of get a closed form for this by the same method. Okay, that's it for today. Thank you very much. Hello everybody, welcome back. In the last few lectures we have seen a lot of things about the binomial coefficient n choose k. For example, several combinatorial identities. We have derived exact formulas for several complicated sums. And we have also seen the big O notation, and one message from the lecture in the big O notation was that sometimes it is better to get a rough estimate of something instead of trying to figure out completely the truth. So sometimes kind of rough estimates are enough, and this is what today's lecture is. We try to determine the size of n choose k. So for two numbers n and k, how large is n choose k roughly? So here's the first lemma. N choose k is kind of sandwiched between these two expressions. Let us try to prove that. So first, the upper bound is pretty easy. N choose k. One of the formulas we have learned is it's n to the falling k divided by k factorial, and n to the falling k is of course less than n to the k, which proves the upper bound. All right? So second, for the lower bound, we have to peek a little bit more into what these things mean. So n to the falling k is the following expression: n minus k plus 1, and here k, k minus 1, and so on, times k, well, times 1 here. Okay, so you see in numerator and denominator both have k terms, so we can somehow chop them up and group these, and so on. And now you see which of them is actually the smallest. Well, the first term is the smallest, so we are on the safe side if we say this is n over k to the k. So we are on the safe side. All right, very simple. In fact, there is a slightly more precise estimate. It's this, n over k to the k is a lower bound, and for an upper bound, you just take the same, but you put in a factor of e here. But I don't want to prove that. I mean, we'll use it occasionally, but I don't want to prove this bound. We'll prove another bound on n choose k later. But let's see a quick application. So for example, n choose square root of n. What is it? Roughly. So first, we have seen as a lower bound, it's n divided by square root to the square root. So this is just square root of n to the square root of n. And as an upper bound, we've seen this is at most e times n divided by square root of n. This is e times square root of n to the square root of n. And you can rewrite this as, for example, e to the 1/2 n square root n, 1/2 ln n square root n. And here this would be e to the 1 plus 1/2 ln n times square root n. So you see, kind of in the suggestive way that I wrote it here, the estimate seems to be pretty precise. But how about something like this? Can we get a good estimate? Can we get a good grasp on how large this should be? So what is our upper bound? Our upper bound is e times n divided by n over 8 raised to the n over 8. And this now is 8 times e to the n over 8. Oh, and this, it turns out, is actually quite bad a bound. It's really bad. I mean, what is this? This is something like, well, you know, I don't even want to talk about it. It's just, you know, this estimate is very bad. So if you have n to k, once k is omega of n, so something like n over 8 or even n over 100 or so, this estimate is very bad. So the estimate e times n over k to the k is a very bad estimate. All right. Well, this is a very bad estimate. Can we get better ones? Yes, we can, but let's do a quick interlude. Let's ask ourselves, of all the binomial coefficients, which is the largest? So which n choose k is largest? So let's see, right? I mean, let's compare n choose k plus 1 and n choose k. And see whether this is larger than 0 or smaller than 0, larger than 1, smaller than 1, whatever. So we get the following. This is k plus 1 factorial n minus k minus 1 factorial. And for this we get n factorial here, k factorial, n minus k factorial. So you see this is n minus k divided by k plus 1. Okay, so this is larger than 1 as long as n minus k is at least k plus 1. So as long as k is at most n minus 1 over 2. And it is, yeah. Okay, so you see basically n choose k, it looks like this. If this is k, this basically means it increases up to here, and then at some point it decreases again. All right, so you can also figure out it is, well, let me think, did I make a mistake? GK, no, that seems fine. Okay, so basically what this proves is the following. Among the binomial coefficients, the largest term is n choose n over 2 if n is even, and if n is odd, then it's the two middle terms you get. So this one and this one. So what does that help us to determine the size? Well, it helps us to determine the size of this binomial coefficient. Because first of all, we know it's at most 2 to the n. Why do we know the upper bound? Well, because this here, by the binomial theorem, is 1 plus 1 to the n is 2 to the n. And this is a sum of n plus 1 terms. So the largest of them must be at least everything divided by n plus 1. And that explains the lower bound. So you know, we've determined the size of this guy up to a factor of n plus 1. Okay, this is good for n choose n over 2, but you know, what does this help us to determine the size of something like n choose k? Well, here's how you do that. So we want to determine the size of this, and we can of course not argue anymore for general k that n choose k is the largest of these terms, but maybe if we are smart we can make it the largest. So suppose I take some value x and I multiply it by x to the k, and I sum up over everything. By the binomial theorem I get 1 plus x to the n. All right, and now maybe we can choose x such that our desired binomial coefficient, so let's say that x to the k, n choose k, is maximized for k equals r, for example. And if we know this, then we have a good approximation for n choose r. So let's see which, let's call this term tk. And let's see which k maximizes tk. So what you can do, you take tk plus 1 over tk. This is x to the k in here we have plus 1. Well, actually, let me write it properly. X to the k plus 1, and down here we have x to the k. So this is x times, and now actually let's go back and simply copy what this is. It's n minus k divided by k plus 1, n minus k divided by k plus 1. And you see tk keeps growing as long as this is at least 1. So tk is less or equal than tk plus 1 as long as this is at least 1, which is as long as, well, actually, let's leave it at this. But now set x to be k over n. Set x to be k over n, and then you see that that x times n minus k divided by k plus 1 is, no wait, x is k divided by n minus k. There you go. Okay, x is k divided by n minus k. So this term here, tk plus 1 divided by tk equals this. Yes. No, wait. N minus k divided by k plus 1. So this is k divided by k plus 1. And you see this is less than 1. On the other hand, tk divided by tk minus 1 is, and now it's again x times what? Now we have to be careful, we have to replace k by k minus 1, so we get this divided by k, so this is k divided by n minus k times this. Which is larger than 1. Okay, and this is super nice because now you see that tk minus 1 is smaller, less or equal than tk, and this is less or equal than tk plus 1. And you actually see, no, wait, tk is bigger. It's bigger than both its neighbors, and if you think about it, this also easily proves that tk is max. So very nice, but what does this help us to determine the size of n choose k? Well, again, if we take the sum here, now let's write j from 0 to n, and choose j, we know which term is the largest. It's the one in the middle. But how does it help us to determine the size of n choose k? Well, here is a very nice trick. What happens if I put in x to the j here? Then by the binomial theorem, this is 1 plus x to the n. And now maybe I can select x such that this term here, let's call it tj, such that tj is maximized by j equal k. So in order to figure this out, we have to compare tj and tj plus 1. So tj plus 1 divided by tj is x to the j plus 1, and choose this. Which is x times n minus j divided by j plus 1. And now we just set x to be k divided by n minus k. And with this, we see that tj plus 1 is larger than tj whenever whenever this is larger than 1, larger or equal than 1. And now you see actually a quick calculation gives you that this is actually the case as long as j is less than k. So T0 goes up all the way to Tk, and then it goes down. So that means Tk is exactly the one that maximizes. So k is exactly the one that maximizes Tk. So therefore, we see the following. This sum is, well, first let's prove this. It's at least the term number k, which is x to the k n choose k. But it's also at most n plus 1 times its largest term, which is also tk. So now you see that n choose k is at most what? Is at most the sum, which is 1 plus x to the n divided by x to the k, and is at least the same thing, well, times this factor of n plus 1. So if you don't care too much about this factor of n plus 1, then this here already tells you the truth. So now let's evaluate this term. And remember, x is this here. So let's again write this down. X is k divided by n minus k. And we know that n choose k is x to the k divided by 1. No, the other way around. Let's go back. Yes. 1 plus x up here to the n divided by x to the k times something that is between 1 divided by n plus 1 and 1. Okay, so now let's evaluate this term here. This is 1 plus k divided by n minus k to the n divided by k over n minus k to the k. Now it's just a calculation. Let's try to get a nice expression here. So this is n divided by n minus k. And this is, well, this is k to the k, and the n minus k to the k gets up here. So now what is this? Well, this cancels, so it's n to the n times n minus k to the n minus k divided by k to the k, and we can nicely write it as n over k to the k, n divided by, wait, here's something wrong. Okay, of course, this is, it's supposed to be k minus n. Yes, k minus n. That's nicer. So we can write it as this, right? Now, what is k? Let's say k is roughly proportional to n. So k is r times n, and r is something like 1 over 8. Then this has a kind of a very nice form. This is 1 divided by r to the rn times 1 divided by 1 minus r, 1 minus r times n. And now let's focus on this term. So this is basically, let me put big parentheses about it and delete the n here and just pull it out. We can write it as 2 to the minus r log r minus 1 minus r log r. 1 minus r. Right? We're just rewriting r as a 2 to the log r. And this beast in here, it's very important. This is called the binary entropy function. This is called h of r. And finally, we have the following compact formula. All right, so let's write up nicely what we have learned. N choose r times n is 2 to the binary entropy of r times n times some number that is somewhere between this and 1. And actually what kind of number this is, it can be determined a little bit more precisely. But you see what you have here, if r is some number, if r is 0.2 or something, this is exponential in n. So this is already so big, so we don't really care about this factor 1 over n plus 1 or something anymore. So for certain values of r, if r is a constant between 0 and 1, this is the best estimate that you can get for the binomial coefficient. And yeah, so this formula you should really keep in mind. Thanks. Hello everybody, welcome to our video lecture on discrete mathematics. In the last few sessions we have learned a lot about the binomial coefficient n choose k, and today I want to show you an application of what we have learned. So the last lecture ended with the following formula for the sum of the falling powers of an integer m. So remember, m to the falling k was defined to be m times m minus 1 times m minus 2, and you continue until you have collected exactly k factors. So your last factor is m minus k plus 1. It's a little bit tricky to remember the plus 1 here, so I always have to think twice to really figure out where I have to stop. Okay, so the application involves a little bit probability theory, but really only vanilla probability theory. So even if you haven't had a course in probability theory, you probably can follow everything I say here. So consider the following scenario. I have the numbers 1 to n, and I select a set of size k uniformly at random. So for example, let's say k equals 3, and I select 3 numbers without replacement randomly. Suppose I select these 3 numbers, and then I let x be the smallest number I have chosen. So in this case, x equals 3. And I want to know what is the expectation of this minimum. Right? So again, the setting is we have n numbers, we select a subset of k of them, take the minimum, and want to determine the expectation of this minimum. So here's the formula for the expectation. It is the sum over all possible values. So here the possible values are from 1 to n, I times the probability that x equals I. So well, this looks simple. So we only have to find out what is the probability that x equals I. Well, this here is it's the number of sets A in n choose k such that the minimum of A is exactly I, the number of these sets divided by, well, the number of all subsets of size k. So now we have to do a little bit of thinking. How many sets are there that have I as a minimum? So I is in there, and then the rest of A is somewhere between here. So well, to the right of I, we have to select again k minus 1 elements. And how many possibilities do we have to do so? Well, how many numbers are there bigger than I up to n? Well, this is n minus I. So it's n minus I choose k minus 1, divided by n choose k. So this is a probability that the minimum is exactly I. Let's see whether we get anything helpful here. So this is n minus I factorial divided by this times n minus I minus k plus 1 factorial. Looks a bit nasty, but let's see. And then I have n factorial here, k factorial here, and n minus k factorial here. And then you see, actually, you can do a bit of cancellation. This and this cancels out, and a factor of k survives. So you get something like this. It's k times n minus I factorial, and then n minus k factorial. And here we have n minus I minus k plus 1 factorial. N factorial. So another point is we might be able to write this in a little bit nicer way, but the problem that remains is, in order to compute the expectation, you see we have this I in front of here. So what you should do, we should sum up over all I times this. Also here. And now I have this very uncomfortable expression. I have I on the one hand side, and then I have n minus I factorial and so on, and I have no clue how to deal with that. So with all that we have learned in the last lectures, I tried to make sense of this expression for maybe half an hour or something. I couldn't go anywhere. So this is a dead end. Maybe we should back up a little bit and try a different route. So let's do that. Here is actually something very important I can teach you about expectation. It's the following. If you have a non-negative random variable that takes integer values, you can rewrite the expectation with this formula. And, well, let's prove that. The expectation is the sum over all I times the probability that x equals I. And now I rewrite that. I rewrite I in this weird way. Actually, we can start with 1 here. I rewrite it as the sum from j equals 1 to I of 1. Now the trick is to just pull in these sums together. So if you look at it, we just sum over all integers j and I, such that j is between 1 and I. So I can as well say I let j run from 1 up to infinity or whatever, and then I sum over all I. And where do I have to start? Well, I have to start at j. And now it's very nice because you see this sum here, we can write as the probability that x is larger or equal than I. Than j, sorry. X is larger or equal than j, and we sum up for all j from 1. All right, so this proves this lemma. The benefit is that in this sum here, we don't have any factor j. We don't have any factor in front of the probability, so maybe it's a little bit easier now to sum up. So let's try it again in our case. So now we have to calculate the probability that x is at least I. So what is this? It basically means all the numbers we select are from this set, and so we just have to count how many possibilities do we have to select k elements from the set. I mean, how large is the set? It's n minus I plus 1. Choose k divided by n choose k. Nice. Okay, so let's see whether we are luckier here. So this is n minus I plus 1 factorial divided by k factorial times n minus I minus k plus 1 factorial. And the n choose k gives us this. It looks pretty similar to what we got before, maybe a little bit easier. So now what is this? This is the k factorial cancels, and what you get is n minus I plus 1 factorial divided by n factorial, and here we have n minus k factorial divided by n minus I minus k plus 1 factorial. Okay, so what is this? Well, this is, we can rewrite it as this. It's n to the falling k. That takes care of these two factors. And to take care of these two factors here, we get n minus I plus 1 to the falling k. So this is the probability that x is at least I. Okay, let's get some more space. So we have seen this is the sum over all I from 1 to n. And now what do we have here? The denominator is n to the falling k. And up here we have n minus I plus 1 to the falling k. Good. Okay, so the denominator, we can just pull it in front of the sum. This is very nice because it doesn't depend on I. And now again, let's do a change of variable. Let's say j is n plus 1 minus I. Right? So now let's see, I runs from 1 to n. So what does j do? Well, if I equals 1, then j equals n. And if I equals n, then j equals 1. So j just, runs from n down to 1. Right? So we basically sum over the same range. But now it kind of looks nicer because we simply have a j to the falling k. And now we apply what we have learned. We have a formula for this, right? What is this? So the sum is, it's n plus 1 to the falling k plus 1 divided by k plus 1. And then, of course, we have to take this denominator here. All right? So what is this? This is 1 divided by k plus 1. And we have n plus 1 times n minus 1. And we go all the way until we have k factors. So the last factor is n minus k plus 1. And down here, we start with n. We have n minus 1. And we go all the way until we have k factors. And everything cancels. And our result is n plus 1 divided by k plus 1. So this is nice. We had a very simple sounding problem, determine the expectation of this minimum. We dutifully calculated what it needed to calculate, namely the probability that x is at least I. We got some messy expressions in the end, but by some magic, in the end, almost everything cancels out, and we have a super nice expression for this expectation. It's just n plus 1 divided by k plus 1. All right, so at this point we could stop and go home, but one of the points I want to tell you here, in mathematics there are often two ways to do something. The first way is just to do the calculation. Don't think too much, just calculate, try to cancel, try to get nice expressions until at some point you find something. And the other way is be lazy, try to avoid calculations and replace calculations by clever thinking. And that's what I want to do in the second half of today's session. I want to prove the lemma again, but now I want to give you a proof where we basically don't have to calculate anything, but we have to think a little bit more. Okay, are you ready? Let's go. Second proof. So what I do is I take a circle, and on this circle I put the numbers 0 up to n. And now what we do is we select k points to be in our set A. So the red points are A. and we let x be the minimum of a. So x is this, and then c, x is simply also the distance from 0 to x if you go clockwise, right? So you start at 0, you go to x, the number of, how should I say, edge segments or something you pass. This is the variable that we are looking for. This is x, okay? So we have the circle, we select k numbers from 1 to n, we mark them red, and we take the distance from 0 to the first one. So this is not very exciting so far. Now we color the vertex number 0, we color it blue. And now observe, now we just take the circle and we forget about where the 0 is. You can imagine we take the circle and we rotate it in some random way. So now we don't know where the 0 is. So the 0 could be anywhere. So we select our set of k red vertices, and then we select where the 0 is. Okay, now the 0 is here, and now the variable we are looking for is just, again, the distance from the blue vertex to the red vertex. So let's now call this x prime, and you see that x prime behaves exactly as x. So we can just as well try to determine the expectation of x prime. And this is easier. Why is this easier? Well, because instead of selecting k red vertices and then one additional blue vertex, we could do it the other way around. So what we are doing now, we select k plus 1 red points out of n. Now out of n plus 1. So we have n plus 1 points, right? Why? Well, because it's the points 0 up to n. This is n plus 1 many. And then we select from this set here, we select k plus 1 points and we color them red. Okay? Now what we are doing, we just pick one of them and color it blue. So we change the color of one of them and make it blue. And then this is what we are after for. This is our random variable x prime. Okay, this is still nothing new, but now comes the trick. We have these k plus 1 red points, and we say y1 is just the distance from the first point. So let's say up here is 12 o'clock, right? So y1 is this distance, and this is y2, this is y3, and so on. So we have now k plus 1 numbers. And to what do they sum up? Well, they sum up to n plus 1, right? And now, if we make one vertex blue, suppose we make this vertex blue, this here, it just means we select this to be x prime. So basically what we do, we take these k plus 1 points, we get these distances y1 up to yk plus 1, and by selecting one of the red vertices and make it blue, we basically say, well, our value x is just, one of these numbers y1 until yk plus 1, and we select it randomly. And therefore, you see we have k plus 1 choices, so therefore the expectation, if we take a random one of them, just must be the average, and the average is just n plus 1 divided by k plus 1. And you see, that's again a proof. Actually, you might think it's not a completely formal proof, but trust me, if you invest some work, you can make everything very formal. But the nice thing is, we didn't do any calculation. The only calculation we did was saying, hey, look, these numbers y add up to n plus 1, and if you select one of them at random, on expectation, it gives you n plus 1 over k plus 1. That's the only calculation we did. So the message to take home here is there might be several ways to solve a problem, and there's basically the, how should I say, well, there's often a way that requires a lot of work, but not too much thinking, and often, and these are the beautiful moments in mathematics, there is a way that requires some clever thinking, but almost no work. And this, whenever possible, is the way I think you should go. Thank you. Hello. Today we will introduce an important bit of notation in discrete mathematics and theoretical computer science, which is called the big O notation. So because this is a big O, it's called the big O notation. As a motivating example, I went to Wikipedia and I took a screenshot of the pseudocode. If you have done some programming before, you will surely see this is a sorting algorithm. It's not the best sorting algorithm, it's actually a pretty bad one. Anyway, it's pretty simple, and let's try to see how many steps this algorithm does. So you see, let's say the size of A of our array is n, then you see that this here, the outer loop, will be performed n minus 1 times. You also see maybe the inner loop will be performed, well, actually, maybe let's say at most n minus 1 times. We don't know. It depends on the number of the iteration, but surely not more than n minus 1 times. And then we have the swap operation here, and this is a little bit weird. I mean, how many steps does this take? And this depends on what? I mean, it depends on how this is implemented in your computer. It could be that your processor has a swap operation that says, okay, take this cell in the memory and tell this cell and then just swap the contents. But maybe it doesn't, and then you have to do, you as a programmer or as a compiler, you have to do something like this. You take a temporary variable and you say, okay, temp is aj, and then you say aj is aj minus 1, and aj minus 1 is temp. And how many steps does this take? Again, it depends. What is a step? Like j minus 1, computing j minus 1 already is a step. So this could be anything here between 1 and let's say 20. I don't know, it really depends on your computer. So if we just add everything up, we see the running time is something like n minus 1 squared times something that we don't really know. Okay, and then maybe there is some additional stuff, right? Let's actually some constant a that we don't know, and there might be some additional stuff, and so on. So the running time of this algorithm is of the following form, and we don't know a, b, c. They might depend on your programming language, on your compiler, on your computer, and so on. But you see that you have something like n squared in your expression. It does not depend on your programming language. It only depends on the algorithm. And this is exactly the purpose of the big O notation. We want to somehow hide the unimportant information. We don't want to think about the implementation details, and we just want to focus on kind of what matters. So formally, the definition is a little bit technical, so let me walk you through it. If f is a function, then O of f is formally a set of functions. It's a set of functions such that this holds. And for this, actually, let me make a little picture to explain it. So we have a function f. Let's say this is f. And then c times f. So c is some constant here. So c times f is simply like this. Okay? And the big O notation says from a certain point on n0, our function g here must be below the pink line. So it could something like g could be something like this. It can be bigger than f, it can also be bigger than c times f, but only for small values of n. So past a certain threshold, n0, it must stay really below c times f. Let's see an example. So we have seen our running time was something like a times n minus 1 squared plus bn plus c. And now this is of course at most a n squared plus b n plus c. And I want to claim that this is at most c times n squared for some c. So how should I choose capital C? For example, choose capital C to be a plus b plus c. And then we see that this expression here is less than an squared plus bn squared plus cn squared, which is c times n squared. So we can conclude that our function f of n, which describes the running time of our algorithm insertion sort, is in O of n squared. So here are some rules for the big O notation. You can take all the time you want and look at them. You can, of course, click on pause. I just want to explain, to illustrate quickly two of them. The second here would, for example, tell us that if G1 is in O of n and G2 is in O of log n, then the product, for example, G1 times G2 is in O of n log n. Also very interesting is kind of the last rule. It's a sort of domination rule. So if G is in O of f, it means that f can just swallow up any amount of G that you add to it. For example, n squared plus 1000n simply is also in O of n squared. At some point, the n squared will simply eat up the 1000n term. Some other rules to bear in mind is the following. Like larger polynomials win. So n to the 10 is in O of n to the 11. The second means exponential functions beat polynomial functions. So n to the 1000 will at some point be overtaken by something like this. It might take a while, but it eventually will. The last is a variation of the second. So if you have something like log n to the 1000, it's in O of, for example, 20th root of n. Okay. The big O has a big brother, which is called the big omega. So what is big omega? Big omega is basically the same thing. It just says at least. So for example, if I have n squared minus 1000n, you see this for small n it's negative, but at some point it will be at least c times n squared if n is large enough, right? You can try to figure out what you have to choose for c and n0. So we can say n squared minus 1000n is in omega n squared. So this says eventually our function grows proportional to n squared. Finally, there is theta, and theta is just the intersection of O and omega. So it means G is in theta of f if it is in O of f and in omega of f. So here is a nice example. You remember from some sessions ago that I derived a formula for the sum from k equals 1 to n of k squared. Now here we have k cubed, but suppose we are not interested in an exact formula, we're just interested in a rough estimate, like how big is it roughly, okay? So what you can do is, we can say, well, I mean, obviously this here is at most the sum from k equals 1 to n of n cubed, because n cubed is always bigger than k cubed. And this you can see is n to the 4. So that basically means that our sum, f of n in particular, is in O of n fourth. Right, on the other hand, our sum is at least the following sum. I can say, well, I start not at k, but I start at n over 2, rounded up. And when I do that, then every term in my sum, so k is always larger than n over 2, so I can say, well, this is at least n over 2 to the third, and I run from n over 2 ceiling all the way up to n. So I have at least n over 2 summons. So what I get is this. And this says that our function, the sum, is in omega of n to the fourth. So now we can conclude our sum is in theta of n to the fourth. So although we haven't derived an exact formula, we can say with confidence it has the same growth rate as n to the fourth. We just don't know the exact formula, but it's roughly n to the fourth. So I hope here you really see the benefit of the big O, big omega, big theta notation, because it can save you a lot of work. It helps you to distill the really important information. Another notation that you often see O of something not used as a set of functions, but as a kind of a placeholder for a function itself. So you see in the literature, you often see things like Gn plus O of something. And what that basically means, it means the difference between f and g is bounded by O of r. So here again, let's take our k to the third example. So you see, what is k to the falling 3? This is k times k minus 1 times k minus 2. So we can see that k to the 3 equals k to the falling 3 plus O of k squared, if you expand this product. And therefore, this sum here is the sum from k equals 1 to n, k to the falling 3 plus O of k squared. So now you see this is the sum from k equals 1 to n of k to the falling third plus this. And we have a formula, we have an exact formula for the first sum. This is, can I remember, this is n plus 1 to the third divided by 3, no, to the fourth, of course, divided by 4. And then the second sum, you can easily see, is bounded by O of k cubed, O of n cubed, sorry, O of n cubed. Yeah. And so you see, this is n to the fourth divided by 4 plus O of n cubed. So this term, again, also has some garbage, but the garbage is n to the 3 plus something of lower power, so we can just move it into the O of n cubed part. And this now has the benefit that we have a much more precise estimate for our formula. Now you see, basically we know it grows like n to the fourth, but now we have also determined the leading coefficient, which is 1 over 4. All right, and this has not been a lot of work, because by using cleverly the big O notation, you really can save a lot of work by saying, well, this is actually a term or a part of it that doesn't really interest me, so you can safely ignore it. And the rules that I have showed you today, they tell you how to safely ignore them. All right, that's it for today. Thank you. Hello everybody. Today we will start with part 2 of this course, and the topic of this part is graphs. So what is a graph? Well, that's easy to answer. For example, this here is a graph. So you see here some dots which are connected by lines. But in graph theory we call them specific names. So this, such a thing here, a point, it's called a vertex. And the plural is vertices. So please don't say vertexes or something. No, no, no. Vertices. And a connection between two vertices is called an edge. That's just the name we give these things in graph theory. Okay, so you see here an example of a graph, but what does it mean? Does it represent anything? So the nice thing about graph theory is a graph can represent a lot of things. For example, it could be that we have a dinner party with 5 guests, Alice, Bob, Charlie, Daniel, and Eve. These are our 5 vertices, and an edge between 2 people means that they have known each other already before this dinner party. So for example, Alice and Bob have known each other before coming to the dinner tonight, whereas Eve and Charlie meet each other for the first time tonight. So this is kind of a relation that can be expressed as a graph. And why are graphs so important? Well, because they appear literally everywhere, especially in all things that have to do with computers, where you want to solve some computational task. One example is this. This is the Shanghai subway network. It's actually kind of the middle part of the city, because Shanghai is a big city. And here, for example, our vertices would be the subway stations, and there is an edge. An edge between 2 subway stations means that there is a direct subway line connecting this station to the next station. So this is also an example of a graph. Another example would be this, which is an illustration of the internet. So here every vertex would be a computer, so most likely a server or an internet router, and an edge between the 2 vertices means that there is a physical connection, maybe a wire or a fiber cable or something like that between the 2 routers. And by the way, the colors in this picture, they represent the physical, the geographical locations. So for example, yellow, I think, is Europe or something. But I don't want to give you any wrong impressions. So these graphs here, they can somehow nicely be drawn in 2D. There are some other graphs that are so huge that you're probably not able to depict them. So let's go back to our dinner party graph. And for now, I just call my vertices 1 to 5 instead of Alice, Bob, and so on. So what is a graph? Mathematically speaking, a graph is a pair VE, where V is the set of vertices, and it's simply a finite set. There is also a theory of infinite graphs, but in this course we basically always stay with finite graphs. And what is E? Well, E is the edge set, which describes which vertices are connected and which are not. And mathematically now, with the notation that we have developed in the very beginning of this course, we can very elegantly say what E is. So E is a subset of V choose 2. So it's a set of size 2 sets of vertices. This might sound very abstract, so let's do it for this graph that you see here. The vertex set is simply the set of numbers 1 to 5. And the set of edges is the following. So it contains 1, 2, because there is an edge from 1 to 2. It contains 1, 4. It contains 2, 3, 2, 5. What else? 3, 4, and 4, 5. So that's clearly a subset of V choose 2. That's our set of edges. And a little bit more of notation. By n, we denote the number of vertices, and by m, we denote the number of edges. So in this example, n would be 5 and m would be 6. All right, that's the formal definition of a graph. So let's look at some more complicated graphs. Some of you might know this puzzle. I think it's called the 15 puzzle, if you want to go to Wikipedia and look it up. So we have this board, 4 times 4 board, and we have 15 tiles which are placed on this board. And now you can move them. You can, for example, move tile number 6 into the empty space, and then you can move tile number 11 up. And of course, you can make everything in reverse. You can move the 11 back where it came from. So how does that define a graph? So let's see. Every possibility how to arrange the tiles on this 4x4 square would be a vertex. So here I only show you 3 vertices, but there is of course many more vertices. And what is an edge? Well, let's say 2 configurations are connected by an edge if they are 1 move apart. So you see here, for example, we can go in 1 step from here to here and back, and therefore we insert an edge. So let's see, this graph is really huge. How many vertices does it have? So the number of vertices is equal, as you can see, to the number of injective functions from the numbers 1 to 15 into the set 4 times 4. You can convince yourself this is 16 factorial, so this is pretty huge. So this graph you can most likely not easily depict on paper. What is the number of edges? Well, with what you know so far, you can figure this out. So you should do that as a homework, or you should just pause the video now and try to figure out what the number of edges is in this graph. Another example of a huge graph would be, for example, this. So this is Rubik's Cube. I actually don't know how to solve it. I don't know how to bring it back into the ordered state. But you can say, if I keep it like this in my hand, then this, as the cube looks like now, that would be a vertex in your graph. And now I make a transition into a new configuration and I can do it back. So I can go both ways. So this would be a new vertex, and these two vertices are connected by an edge. So two states are connected by an edge. If I go from one state to the other state in just one move. So this is a huge graph, and it probably has a quite complex structure. Another example of a graph that is only implicitly given, and you usually don't draw it, is the so-called Kneser graph. I'll let you plow through the definition. What I want to show you, just as an illustrative example, is the Kneser graph 5, 2. So here the vertex set are all element 2 subsets of the numbers 1 to 5, and two sets are connected by an edge if these sets don't intersect, so if they are disjoint. Here the graph would look like this. Well, this doesn't look too nice, but we can actually make it very, very nice and symmetric by putting the vertices in kind of a different order like this, and then the graph looks like this. This is also called the Peterson graph. All right, so we have seen a lot of examples of graphs. What's next? There are some classes of graphs that appear over and over again, and we just have to go through them quickly and introduce the names such that you understand in the future when I refer to them what I'm talking about. The first important class of graphs are the so-called complete graphs. Complete graphs. Well, they are called complete because every edge that could possibly be there is there. So the set of edges is simply everything. It's the whole V choose 2. So this would be K6, that would be K5, and so on. And you see K1 just consists of some one lonely vertex. So these are the complete graphs. Another important graph class is cycles. A cycle is just a graph that looks like this. And well, this would be Cn, where you have, let's say, n vertices, 1, 2, 3. Here's vertex I, here's vertex n minus I, here's vertex n minus 2. So cycles are also very important. And last, this is the class called paths. Well, they are called paths because they look like paths. So this is a path of length 2. Be careful, the length of a path is not the number of vertices in it. It is the number of edges in it. That's kind of a source of confusion, so we should be kind of clear about that. That's P3. This is 1, 2, 3, 4, 5. That's P5. And this is P1. And this is P0. And just as a remark, this is actually equal to K1. And this is equal to K2. But of course, this is equal to K3 because K3 looks like this. It has all the edges on 3 vertices. And so on. So we have defined complete graphs, cycles, and paths. And these are arguably the most important graph classes. That's it for today. Next time we'll do something interesting with graphs. Thank you for today. Hello everybody, welcome to our online course on Discrete Mathematics and to our second lecture on graph theory. Today The first topic I want to talk about is the following question. When are two graphs the same? This may sound like a stupid question, but actually it's not. For example, this graph and this graph. They don't look the same, but let's take a close look. Are they the same? Well, let's see our mathematical definition of a graph. What is the vertex set? Well, the vertex set is A, B, C, D. And you can see all edges are there. So the edge set is V choose 2. And in the graph on the right-hand side, it's just the same. It's the same vertex set and it's the same edge set. So yes, we conclude these two graphs are the same. They are just drawn differently. The same graph. Okay, how about these two graphs? Certainly they don't look like each other, but if you look very closely, in some way they are the same, but not quite. Because here, what is the vertex set? The vertex set is the set of numbers from 0 up to 7, and here the vertex set is the power set of 1, 2, 3. So obviously, already the vertex sets are not the same. So mathematically speaking, it's not the same graph. So far, so easy. Again, these two graphs you can see are the same, but this graph is different because, for example, here you have an edge from A to C, but in the last graph you don't. So we see these graphs are the same, but these graphs are not the same. But in some way, all these graphs look the same. The only way they differ is the names we gave to the vertices. But if for a moment we ignore the names and we just want to look at the structure of a graph, we could argue in some way they are all the same. And this way of thinking, in some way they are all the same, can be made precise mathematically, and that's what we are going to do next. So now we'll give a precise mathematical definition of what it means to look the same. That's called a graph isomorphism. So take your time to work through this definition. What I now want to do, I want to illustrate this definition at an example. So remember, you can always hit pause if I'm going too fast and really read through my slides. But I don't have to sit there and watch you doing this. Okay, so I proceed and show a graph isomorphism at this example. So here we have two graphs. As we have seen, they are not the same, but here is an isomorphism. So I take the vertex in the left graph and I map it to the vertex A in the right graph. So it's basically something like this. And then I take the vertex C and I map it to D. I take B and I map it to C, and I take D and I map it to B. So what you have here is we have a graph VE, and we have here a different graph on the same vertex set, VE prime. And this thing here, well, this is a function from V to V. It's bijective and it satisfies all the conditions of a graph isomorphism we defined on the last slide. So this is an isomorphism. Let's take a little bit more complicated example. These are this cube on the left-hand side and this double square on the right-hand side. What can we do here? Well, we could, for example, start and say, well, this vertex should map to this vertex. So we take the empty set and we map it to the vertex 0. Okay, so how should we continue? What should we do with the 1? Well, one thing is it should be mapped to a neighbor of 0 because it's a neighbor of the empty set in the graph to the left. So now we have a choice between 1, 2, and 4. Now we have to make a choice. Maybe we make a mistake. So let's say we map the set 1 to the vertex 4. Okay, so let's write that down. This is the set 1. And let's map the set 3 to the vertex 2. And the other neighbor, the last neighbor, which is this here, we should now map to the last neighbor of 0, which is 1. Here you go. And now you can see whether you can finish the isomorphism. Figure out how you should map the vertices on the left to the vertices of the right to get an isomorphism. All right, do this now. When you're done, come back to me. The concept of isomorphism is important because it allows us to abstract from the actual representation of a graph, either how the vertices are named or how we draw the graph in the plane. So for example, you can see this graph. In this graph, they don't look alike, but they are isomorphic, as we have seen. Also, this graph is isomorphic. I encourage you to prove this. And also this graph. So these are 4 different ways to draw the same, not the same, but isomorphic graphs into the plane. So maybe take your time and really figure out the isomorphisms between these 4 graphs. That's it about isomorphisms for today. The next thing is I want to talk about the degree of a vertex. If you have a graph such like this, the degree of a vertex is simply the number of edges this vertex participates in. So formally, the degree of a vertex is the number of edges in E such that U is in E. That's the degree of a vertex. So we have seen this graph before. That's the Kneser graph, 5, 2. And here you can see the degree of every vertex is 3. In such a graph, we call it 3-regular. And in general, D-regular would just mean that the degree of a vertex, of every vertex, is D. So regular graphs are also very important. Here is another D-regular graph, 3-regular. This is the graph we've already seen a couple of times. The most fundamental fact about the degrees of the vertices in a graph is the so-called handshaking lemma. I let you figure out why it's called the handshaking lemma. So it says if you add up the degrees of the vertices, you get twice the number of edges. Yeah, you can try to come up with a proof yourself. If you're too lazy for that or too impatient, I will show you one. So here is an example graph. And because it's Christmas time right now, when this video is being shot, I want to give Christmas cookies to the edges. So every edge gets 2 Christmas cookies, and I place them at the 2 ends of each edge. Well, in reality, Christmas cookies are not really red, but who cares? Good, so every edge has received 2 Christmas cookies, so I have distributed a total amount of 2e Christmas cookies. So now the vertices come and they eat up the Christmas cookies, and every vertex eats up all the Christmas cookies that are placed next to it. So vertex U eats deck of U cookies. And you see in the end all the cookies are eaten up. So how many cookies are eaten? Well, this is just the sum of all degrees. So the sum of all degrees equals 2e. All right, that's the handshaking lemma. Now the handshaking lemma has a very innocent corollary which has surprisingly powerful applications. Maybe in 6 lectures from now, we will see 2 such very nice applications. So the corollary states the number of odd degree vertices is even. Let's see in this graph, this vertex has odd degree and this has odd degree. So here we have 2 odd degree vertices, which is an even number. So how do you prove this corollary? Well, you just take this equation and take it modulo 2. So what you get then, the right-hand side is clearly 0. You see that 0 is congruent modulo 2 to the sum of all degrees. And an even degree is congruent modulo 0, and an odd degree is congruent to 1. So this is congruent to the number of odd degree vertices. That's the proof. All right? Last topic for today, the so-called score of a graph. The score of a graph is basically just a sequence of numbers that describes the degrees of the vertices. So here I have a graph G, and the score of G would simply be 1, 1, 2, 2, 3, 3. So we take the degree of every vertex. This gives us a sequence of integers. We sort them from smallest to largest. This is the score of a graph. Now, the interesting question is, which number sequences can appear as the score of a graph? Let's see some examples. Can a graph have the following score? The answer is obviously no. You see, the graph has only 2 vertices, but here we have a 7. So there are not enough vertices that could be neighbors of this vertex. This is clearly impossible. How about this? This is less obvious, but if you look at it, we have 3 vertices of odd degree, but we have just learned the number of odd degree vertices must be even. So this is also impossible. So now the homework for you is the following. Find other impossible sequences. And of course, you should look for non-obvious sequences. You should look for sequences that are impossible, but it's really not that obvious that they're impossible. The other is, if 2 graphs are isomorphic, then they have the same score. I should have introduced this earlier. This symbol here just means G and H are isomorphic. So this equality sign with a tilde above it. And your last homework is find G and H such that they have the same score, but they are not isomorphic. All right, good luck with this homework. In the next lesson, we'll actually see a characterization of sequences that can appear as the score of a graph. That's what we'll do next time. Thanks for today. Hello, welcome back. The last thing we talked about in the last session was the score of a graph. As a quick reminder, if you have a graph like this, and you write down the degree of every vertex, 2, 2, 3, 1, then the score is simply the degree sequence. In this case, it would be 1, 2, 2, 3. And remember the homework I gave you last time? I hope you did it, at least tried it. If not, you should hit pause now and try it. And once you're done, you can get back to me and hit continue, hit play. So today we will come up with a characterization of possible sequences that can appear as the score of a graph. As a warm-up, let's look at some sequences. Can this appear as the score of a graph? Think about it. Well, the answer is no, because one vertex must have degree 4, but there are only 4 vertices. So this degree 4 vertex needs at least 4 other vertices to, to connect to. So this is not possible. How about this? It doesn't seem so impossible, but by the handshaking lemma, you see the number of odd degree vertices should be even, but here in this sequence it's odd. So also this is not possible. How about this? Let's see. Well, there are 4 odd vertices. That's fine. Nothing else seems inherently impossible. So let's try. How should we try that? So we put 6 vertices. We need 6 vertices because it's a length 6 sequence. We put 6 vertices into the plane, and then we write down the degree every vertex should get. And then we just start. This vertex has 5 neighbors, so we connect it to everybody else. And then you see this vertex is already happy. It has 5 neighbors. This is already also happy. It has 1 neighbor, needs 1 neighbor. This still needs 1 more neighbor. These still need 2 neighbors. Okay, so what should we do now? Well, let's just take a vertex that still needs the highest number of neighbors. For example, this, and let's give him 2 neighbors. Now this vertex is happy. This vertex is happy. And this vertex, oh, damn it. You see, I made a mistake. Okay, so let's undo it. We cannot do it so easily. I should delete this and this. So this vertex down here still needs 2 edges. So one thing we should do is we should make sure it connects to the highest degree vertex. It's actually good that I did a mistake because now we see it. And maybe to this vertex. So now this vertex is happy, this vertex is happy, and this vertex still needs 1 edge. And this vertex up here still needs 1 edge, so we just connect them. And there you go. Now you have a graph of score 1, 2, 2, 3, 3, 5. So what have we learned? Well, we can find a graph by just trying, but we have also seen we have to be careful because you see I made a mistake. This was really not planned. This was not something that I set up to say, okay, it's good to show my students a mistake for pedagogical reasons. It's just really happened to me. I made a mistake. So let's see one more example. The score is 1144666. Also, it doesn't look impossible, right? There seem to be enough vertices. There are 2 odd degree vertices. I don't know. It seems fine. So let's try to find a graph with this score. So here I put the vertices, and again I write down the degrees these vertices should have. Let's pick one vertex of degree 6, and let's give this vertex 6 edges. And as a rule of thumb, we connect it to the highest degree vertices. So we connect it here, here. This kind of makes sense because these vertices also want a lot of edges. So we should give them the edges in the very beginning, right? Okay, so we do it like this. And one more. 1, 2, 3, 5, 4, 6. Okay, that's enough. This vertex is happy, this vertex is happy, this still needs 5 edges, this still needs 5, and these still need 3 edges. Okay, so next we pick a vertex of highest degree, 5, and we connect it to 5 vertices of highest degree. For example, this vertex, 1, 2, 3, 4, 5. Now let's see. This vertex is happy, this vertex is happy. This still needs 2 edges. This needs 2, this still needs 4, and this still needs 2. Okay, so all vertices are happy except these 4. So now I'm left with a task of constructing a graph on 4 vertices with score 2, 2, 2, 4. And as you can see, this is actually impossible because there are not enough vertices, right? 1, 2, 3, and where should the 4th edge go, right? Okay, so this is not possible. But wait, maybe I made a mistake. So maybe we just did a mistake and we connected a vertex to some vertex that we shouldn't have connected it to. Well, it turns out this method that we just applied, it always gives you the correct answer. It always finds a graph if there is one, and it returns failure if this graph score is impossible. So here is the algorithm formally. Find graph. So first we sort these numbers, and then we define di prime to be this. We try to find a graph of score d prime. And if this graph doesn't exist, then we also return failure, so we return a null pointer or something. But if it exists, let's say this is our g prime, what we do is we create vertex n and we connect it to as many vertices as we have to. And you can see this new graph G has exactly score d1 up to dn. Okay? That's the graph score algorithm. So here's an observation. If this algorithm returns a graph, then it has the correct score. Now the more interesting question is, if there is a graph of this score, will our algorithm find it? Well, it would be unreasonable of the algorithm to really do that, because there could be several graphs with this score, and the algorithm, of course, doesn't know which one we mean. So the meaningful question is the following. If there is a graph with a score, will the algorithm find some graph with the same score? And here the answer is yes. And now we will prove that. This is proved by the following graph score theorem. It says you have a graph, you have a degree sequence D, and you define D prime by the slightly awkward definition. It will become clear during the proof what this is. And then it says the score D is possible if and only if D prime is possible. Oh, and by the way, if we go back a little bit, we have a recursive algorithm here, you see. So I should specify what are the base cases. Otherwise, the recurrence would run infinitely. So what are the base cases? When can we just return yes? When can we just return a graph? Or when can we return failure? Well, I'll let you figure this out. Maybe you have to run some examples to figure this out. Okay. So this theorem says D is possible if and only if D prime is possible. So here's how we do that. Let me copy the theorem. D is possible if and only if D prime is possible. We have already proved half of it. We have shown if D prime is possible, then D is possible by just adding another vertex. So this we have already proved, so now we have to show if D is possible, then D prime is possible. And this will follow immediately by the following claim. If there exists a graph G of score D, then there also exists a graph G of the same score in which the last vertex n, which has degree dn, is connected just to all the previous vertices. And with this claim, we can just take G and remove the vertex n. We get a graph G prime, and you see what is the score of G prime? Well, it's exactly D prime. Because all these vertices here that are neighbors of n, which are the vertices which are the vertices n minus dn up to n minus 1, their degree now decreases by 1, and the rest of the vertices stays the same. The degree doesn't change. Okay, so you see, if we can prove the claim, then we can prove the theorem. So now we have to prove the claim. So let's copy the claim. J of G among all graphs with this specific score, then J of G equals dn. So here's the proof. Suppose not. So let's suppose that J of G is less than dn. And our goal is to derive a contradiction. And that proves the claim. So suppose j of g is less than dn, then let's draw our graph. So here's vertex n, here's vertex n minus 1, here's vertex n minus j, here's vertex n minus j minus 1. So n is connected to this vertex and to this vertex and everything in between, but crucially not to n minus j minus 1. Let's actually give this vertex a new name, x, because it will appear very often. So xn is not an edge. But of course, the degree of n is dn, which is larger than j, so there must be some vertex y such that n is connected to y. Now comes a kind of counting argument. Note that our vertices are sorted from left to right in ascending order of their degree, so this means the degree of y is at most the degree of x. But this means, since y is connected to n but x is not, there must be a third vertex. Let's call this vertex z, which is connected to x but not to y. So there exists a z such that xz is an edge and yz is not an edge. But now look what happens if we add the following edges. We add an edge from y to z, and we add an edge from n to x, and we remove this edge, and we remove this edge. Then we get a new graph. Let's just denote it like this: g plus nx plus zy minus xz minus yn. So the first observation is that j of h is larger than j of g. And second, you can see easily it has the same score. And there you have it. There you have our contradiction, because we assumed that g maximizes j. But now we constructed a graph that has a higher value of j. That's a contradiction, so g must already have a j value of dn. And this proves the claim, and as we have seen before, this proves the score theorem. We're almost done. There is some homework for you. Is there, oh, damn it, that's, how should I write it? I should write it like this. Is there a graph that has score 2 to 4? Well, obviously not. But how about this graph? Well, now you should shout at me in protest and say, well, this is not a graph. A graph, by definition, can have only one edge between two vertices, because the set of edges is a set of these two element sets. Well, okay, but still, let's call this object a multigraph. I don't want to formally define what it is. It's just a graph that can have parallel edges between vertices. And you see, this multigraph has score 2 to 4. So now your homework is to come up with a characterization of possible scores. Which scores are possible for multigraphs? So basically what I want you to do, I want to play around with multigraphs and ideally come up with an analog to the graph score theorem and the graph score algorithm that we have seen in today's lecture. And actually, to give you some hope, I think for multigraphs the answer is much simpler than for graphs. So it should not be as difficult as in today's lecture. Good luck, have fun with the homework, see you next time. Thanks. Hello everybody. Today we continue with graph theory, And the topic of today's lecture is subgraphs, path, and connectivity. So here is a graph that we have already seen, and observe what I'm doing now. I'm selecting some of the vertices, let's say kind of the right half of this graph, and I select some of the edges that run between these vertices. Maybe like this. So what I get here is a subgraph of the big graph. Formally, V prime E prime is a subgraph of VE if V prime is a subset of V and E prime is a subset of E. Okay. So again, here is the graph, and now we look at a different kind of subgraph. Again, I select some vertices. But now let's say the rule is I have to take all the edges that run between these vertices. So I have to take this edge, I have to take this edge, this edge, this edge, and this edge. So I have a choice which vertices I take, but then I have to take all the edges between these vertices. This is called an induced subgraph. Here is the definition. It reads kind of technical, so V prime is a subset of V, and E prime is now simply the edge set intersected with everything that lies within V prime. And you see, if you give me the set V prime, that already determines the induced subgraph by just setting G of V prime induced by V prime to be the following graph: V prime and E intersect with a set. Okay, so as an example, as we have seen, if my set is, for example, this, that's V prime, and then this is G induced by V prime. That's the induced subgraph. Okay? So there is a difference between a subgraph where I can take an edge or I don't have to take an edge, and the induced subgraph where I have to take every edge that run between the selected vertices. A specific type of subgraphs are paths. So if, for example, I select these vertices and these edges, I get a subgraph which is a 1, 5, 4, 1, 2, 3, 4, 5, which is isomorphic to P5, to the path of length 5. And note, this is an example of a subgraph that is not an induced subgraph because I didn't take this edge and I didn't take this edge. But still, you see, it's a subgraph and it's isomorphic to a path. So we just say G contains P5. We say G contains a path of length 5, okay? Because it does. That's a path. And paths are important because of the following definition. If there is a path from every vertex to every other vertex, so you can go from everywhere to everywhere else, maybe by quite long paths, then we say the graph is connected. So connected means you can go from everywhere to everywhere else. And here's an observation that is almost trivial, but maybe you should take some time to prove it. If G is not connected, then it consists of two or more connected parts. In other words, you can partition the set of vertices into two parts such that no edge goes from V1 to V2. So let me show an example for the last lemma. Here you have a graph which is not connected because you, for example, cannot go from this vertex to this vertex. And of course, I can partition my vertex set into two parts. Okay, that's very easy. So is connectivity an easy problem? Well, it's not too difficult, but don't be fooled. So in this graph, for example, we just see that it's not connected because we drew it nicely. But how about this graph? Well, can you go from here to here? It's probably not difficult to find out, but it's not obvious if you look at it. How about this graph that we have seen a couple of lectures before, where this is a vertex and an edge connects a vertex to a neighboring vertex, which just one of these configurations that is one move apart. So this would, for example, be an edge. This would be a neighboring vertex. That's a third vertex, and that's the second vertex again. This graph on many, many vertices. Is it connected? Try to think about it. But you can see it's not always obvious whether a graph is connected or not. Now, how about this graph? This doesn't look too complicated. It is in the plane. We can see everything of it. Is it connected? Well, we can try to find out. But here, I can clearly demonstrate it to you that it's not connected because I can take this part and move it apart, and then you see it's not connected. All right, so let's talk a little bit about algorithms. How can we find out whether a graph is connected? There is a very simple algorithm. It's called depth first search. So it does the following. Given a graph G, we start at some vertex U, and we mark U as visited. Just that later we see that we have already visited U. And then what we do for all neighbors of U, we check whether V is already marked, and if not, we recursively call depth first search and continue. And the point is that in the end, which vertices are marked? Well, the marked vertices are exactly the vertices that are in the same connected component as U, so such that there is a path from U to V. So let's do depth first search at an example. Here is again the graph from before. So let's start here. This is vertex number 1. And now it iterates over all its neighbors, and it sees this is not yet visited, so we call it recursively, and now we are here. So technically, the way I implemented it, this would now check whether the vertex up here is already marked. Yes, it's already marked. So we go to the next neighbor, and we mark it. This has no more neighbors, so we go back. This has another neighbor, so we explore it, go up here. We try to go to this neighbor, but we see this is already marked. Well, let's actually give the numbers. Vertex 1 is already marked. So we go up here, mark it, and call it 5. 5 has no more neighbors, so we go back to 4. 4 has no more neighbors, so we go back to 3. We go back to 2. 2 has another neighbor, which is this. 6. And now you see the red vertices are exactly the vertices that are in some way connected to 1. That's depth first search. And here's the theorem. It's also obvious if you think about it. If you have a graph, then you can partition the vertices in such sets that each G, Vi is connected, and there is no edge between Vi and Vj. And these are called the connected components. And there is a little bit linguistic ambiguity because sometimes we call the vertex set the connected component, sometimes we call the induced graph the connected component. So pictorially, here is an example. Here is a graph. And now by these colors, black, green, red, and blue, I show you the 4 connected components of this graph. All right, these are the connected components. And that's it for today. Thanks. Hello everybody, welcome to today's lecture. In the last lecture we have introduced the concept of connectivity, which is a very important concept in graph theory. Today we will talk about a related concept, namely cycles and trees. First of all, I want to tell you what a cycle is. A cycle is something like a path with one difference. We go, and we return to where we start from. So you see here, what we get is a subgraph which is isomorphic to the cycle of length 5. So we just say G contains C5 as a subgraph. Of course, this graph contains many more cycles. It contains a lot of copies of C5. For example, I don't know, here, 1, 2, 3, 4, 5. Another copy. So it contains many copies of C5, contains a lot of cycles. This graph obviously don't does not contain any cycle, so this graph is called acyclic. Acyclic means it doesn't contain any cycle. Then again, this graph is acyclic too, but it's not as obvious. So now what you should do, you should go back to the lecture of last time and look at the algorithm depth first search. This was the recursive algorithm that explores the connected component of a vertex. And if you adapt, if you make some slight changes to depth first search, you will come up with an algorithm that finds a cycle in a graph if there is one. Or it tells you that the graph is acyclic. So really go back and try to come up with a recursive algorithm that runs in linear time, so it's very efficient, and it detects whether the graph is acyclic or cyclic. So we have two concepts. One is connectivity. A graph can be connected or disconnected. And the other is acyclicity probably. Anyway, so a graph can be cyclic or acyclic. So we have this table with 4 cells. Now let's fill it with examples. This graph is connected and cyclic. This is connected and acyclic. This is disconnected and cyclic. And this is disconnected and acyclic. And today we are very much interested in the graph that is acyclic and connected. And this is called a tree. So here is the definition. Connected acyclic graph is called a tree. Why is it called a tree? Well, because it looks like a tree. Actually, you get a bonus point if you figure out where this picture was taken. Here is an innocent observation. If you have an acyclic graph, maybe it's not a tree. But if it's not a tree, then it has several connected components, and every connected component is a tree. Right? So either an acyclic graph is a tree, or it consists of several trees. And in this case, we call it a forest. And why is it called a forest? Well, because it looks like a forest. It's a set of trees. Okay? So trees, forests. Here is a theorem that sounds obvious, but in order to prove it formally, it takes a little bit of work. And that's actually what I want to do with you today. I want to prove this theorem. So it says if you have a graph on n vertices, then the following 3 statements are equivalent. The first simply says that G is a tree. The second says it's connected, but it has at most n-1 edges. And the last says it's acyclic and it has at least n-1 edges. Okay, let's start. First, let's see that 1 implies 2 and 3. So our goal is to show a tree has n-1 edges. So we can prove this by induction. If n equals 1, well, then it's not too exciting. Our graph just looks like this. This is certainly a tree, right? It's connected, it's acyclic. It has 1 vertex and 0 edges. Okay, so the step let's say v of g equals n, and n is at least 2. So the first claim is every acyclic graph, well, let me think. Every acyclic, no, let's say every tree. Okay, every tree. Oh, come on. So, okay. Every tree has at least 1 vertex of degree 1. So, how can we prove this? Well, we just take a vertex, and because we assume that n is larger than 2, there must be another vertex. So this vertex that we see here must have at least 1 edge, let's say like this. Otherwise the graph would be disconnected. Okay, so it looks like this. And now what we do, we just start here and we walk. And if this has more than one edge, then we can continue. And we can continue. But, you know, since n, the number of vertices, is finite, this process must end at some point. And there are two cases how it can end. Well, it could be that we go back to a vertex that we have already seen. But you see, this cannot happen because this would be a cycle. And we assume that our graph doesn't have a cycle. So this cannot happen. So the only way this process can end is that we run into a dead end, which just means a vertex of degree 1. Okay, so this proves the claim every tree has a vertex of degree 1. And this is called a leaf. So now we are ready to prove that 1 implies 2 and 3. We have to prove that actually a tree, if G is a tree, then it has n minus 1 edges. So here is how we do it by induction. We take a vertex of degree 1, and here's the rest of the graph. And now we say G prime is G minus this vertex u. And we can see G prime is connected. Removing a vertex of degree 1 doesn't destroy connectivity, that's easy to see. And second, G prime is acyclic. Obviously, by removing a vertex, you cannot create a cycle. Therefore, by definition, G prime is a tree. And how many edges does it have? Well, by induction, it has n minus 2 edges because it has n minus 1 vertices. And therefore, how many edges does G have? Well, one more than G prime because it also has this edge. So E of G is n minus 1, and we are done. Nice, right? Okay, simple inductive proof. So this proves that 1 implies 2 and 3. So next, let's see that 2 implies 1. So suppose G is connected and it has at most n minus 1 edges. The first claim is again, there exists a vertex u of degree 1. But now the proof is different. Suppose not. What can we say about the sum of degrees? Well, we know it's 2 times the number of edges by the handshaking lemma. We also know it's at least 2 times the number of vertices, right? Why? Well, because no vertex has degree 1 by assumption, and also no vertex has degree 0 because our graph is connected. So every vertex has at least is at least adjacent to 2 other vertices. It has degree at least 2. So now we see E is at least V. But that's a contradiction because we assumed that our graph has at most n minus 1 edges. All right? So this proves the claim there must be a vertex of degree 1 by a simple counting argument. And now we play the same game. We take our vertex of degree 1, we define G prime to be G minus u. We see by induction that G prime is a tree. Why? Well, because it's connected and it has at most n minus 2 edges. So it is a tree and therefore it's acyclic. And therefore G is acyclic. And we know that G is connected, so G is a tree. So 2 implies 1. All right, now we are ready for the third part, which is the easiest. If G is acyclic and it has at least n minus 1 edges, well, we know actually that G is VE and it contains several connected parts. So let's say V1 up to Vk are the connected components. So now we know that V equals V1 up to Vk. And we know that E equals E1 plus Ek. We also know that each GVI is connected and acyclic, because G is acyclic, so the induced subgraph is also acyclic. So it is a tree. So it has Vi minus 1 edges. And therefore we see that this is actually V minus K. But by assumption, because we assume 3, this is at least n minus 1. So this means K is at most 1. So it means it has at most one connected component, but of course it has at least one connected component. So we can say it has one connected component. But this is nothing else than to say that it is connected. So G is connected. Oh my god, I think my computer is crashing a little bit. Anyway, okay, so G is connected. And therefore it's a tree. So 3 implies 1. So we're done with the proof of the tree theorem. A last concept that I want to introduce today, because we will talk about it extensively in the next few sessions, are walks and closed walks. So I already showed you what a path is and what a cycle is. And now a walk is something like a path. So for example, I can go from 1 to 3, right? Then to 7, then to 5. I can go back to 1, to 0, and to 2. So this is not a path, because a path shouldn't intersect itself. But this is a walk. So a walk is a sequence of vertices u1, u0, u1, u2, up to uk, such that ui minus 1 is an edge. And k is the length of the walk. And if u0 equals uk, so basically we end up where we started, then it's called a closed walk. So this is not a closed walk. Let's make it a closed walk. We can go to 6, 4, 5, and back to 1. This is a closed walk. Right. And here I leave you with this innocent observation. Every path is a walk. Not every walk is a path, but if you can find a walk from u to v, then there is also a path from u to v. You just can cut out the loops that your path makes, and you get a path. All right, next time we will talk a lot about closed walks and walks. Thanks for today. Hello everybody! Remember a couple of sessions ago we introduced graphs and the concept of graph isomorphism. So today I want to talk about the isomorphism problem on trees. Remember, I showed you a lot of different graphs, and the question is, are they really so much different? So for example, here there are 4 graphs. I claim they are all different. Now for this graph here, in this, it's pretty obvious that they are different because they are over different vertex sets. But for the first graph and the second, it's not so easy. However, you see this graph has an edge from 0 to 4 and this graph doesn't. So therefore, these graphs are also not the same. However, we have seen they are all isomorphic. They are the same, it's just that the vertices have different names. Formally, that's the concept of a graph isomorphism. Informally, it means G and H differ only in the name of their vertices. So that's cheap talk, right? I mean, I can make this definition, it's a very clear definition. I say they only differ in their names. However, to really determine, to see whether there is a true difference or they only differ in the names, it's much more difficult. Just to give you a taste that it's not so simple, look at this picture. You have a couple of graphs. All of them have 10 vertices. Are they the same? Are they isomorphic? Are they not? Okay. I'll let you figure it out by yourself. I just want to get you started. And I want to claim that actually these two guys here are different from the rest. Why? Well, you see here, each of them has a 4-degree vertex, whereas the other are all 3 regular. So they are not isomorphic to the others. But are these two isomorphic? How about the remaining 4? Well, that's a good exercise for you. So for each of them, you can come up with a rather simple argument why they are isomorphic or why they are not. However, the question is there always a simple argument that tells you, well, these graphs are not isomorphic because blah, 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 blah. This is actually not known. So determining whether 2 graphs are isomorphic is whether you can do it efficiently, it's an open problem. Maybe if we restrict our attention to a simpler graph class, maybe we can do something. And that's what we're going to do today. We talk about the isomorphism of trees. So here I have 2 trees. Let's give the vertices names. And now I want to convince you that they are actually isomorphic. And I do that by naming the vertices in the right tree in a way such that the isomorphism becomes evident. So the top vertex here, I think this should be vertex number 3. This is 4, 5, 6, 1, 2, 7. There you go. Stare at it long enough and you see that these trees are really isomorphic. But how can we algorithmically find this out? What we need is we need more structure. So we defined a tree to be a graph that is acyclic and connected, but now let's add a little bit more structure. Let's define rooted trees. So you have a tree and you single out one vertex to be the root vertex. Okay, that's a formal definition. And now we say 2 rooted trees are isomorphic if there is an isomorphism that also maps the first root to the second root. For example, here you can easily see that these 2 here are isomorphic as rooted trees, but these 2 are not. For example, here the root has 2 children that are leaves, and here this only has 1 child, which is a leaf. Okay, so as rooted trees, they are not isomorphic. To come up with an algorithm, we need even more structure. So we need to talk about not only about children, but we need to talk about what is the first child, what is the second child, and so on. That means we need an ordering on children. Something like this. Okay? So formally, an ordered tree is a rooted tree together with an ordering, a linear ordering for every inner vertex. So every inner vertex knows what is its first child, second child, and so on. That's an ordered tree. And 2 ordered trees are isomorphic if you find an isomorphism that maps the root here to the root there, and also preserves the ordering of children. And now if you have 2 ordered trees, it really becomes easy to check whether they are isomorphic. So you see here, these trees are isomorphic as ordered trees, but these here are not. Because here the first child has 2 children, and here the first child doesn't have children. Okay, so as ordered trees, they are not isomorphic. The idea is, if you have an ordered tree, we can encode it in a way that from the encoding we can reconstruct it. So it's we can reconstruct our tree, and 2 isomorphic ordered trees map to the same sequence. And we can do it efficiently, and this gives us a way to check isomorphism. So if you are given 2 ordered trees, we simply compute the encoding and compare whether these 2 strings are the same. So here's how we're going to do it. We start above the root, and then we do depth first search. We enter the root, and every time we go down, we output a 1. So we go down, We output a 0. If we go up, we output a 1. Now our depth of search goes back to the root. That's a 1. We go down to 0. We go down again. It's again a 0. We go up. We go down twice. So 2, 0. We go up 1, 2, 3 times. We go down and we go up twice. And that I call pi of t. So pi of t is the encoding of an ordered tree. Actually, let me give you a recursive algorithm that tells in general how to encode such a tree. Here it is. If t is a single root with no children, you return 0, 1. Else, t consists of a root vertex and subtrees t1, t2 up to tk, and you return 0, pi of t1 up to pi of tk, and 1. Okay, that's a recursive algorithm to compute an encoding. And the observation is, if you have two ordered trees, they are isomorphic if and only if the encoding is the same. All right, how do we encode rooted trees? Note, if you have two trees that are isomorphic as rooted trees, but not as ordered trees, like these trees you see on the slide, the encoding will be different because the children have a different ordering. So how can we do that? Well, here is an obvious trick. Whenever we recursively compute the encoding of the children, we then sort them, let's say from smallest to largest or something, these strings, and then concatenate them. So by sorting first, we make the ordering of the children irrelevant, and therefore it will become an encoding of rooted trees. So for example here, these subtrees all have encoding 0, 1. This has encoding 0, 0, 1, 1. This has 0, 1. So here we get something like 0, 0, 1, 0, 0, 1, 1, 1. Let's call this x. So here we get something like 0, 0, 1, x, 0, 1, 1. Whereas down here we get something else. Here again we get x because this is actually the same subtree. So here we get 0, x, 0, 1, 0, 1, 1. Okay, so these two encodings are the same. But now the trick will be when you recursively compute the encoding of your children, you would sort them and then you stick it together. So you get the following algorithm. It looks very similar. If t is a single root, you return 0, 1. Else, t looks like this. You have subtrees t1 up to tk, and you compute pi I to be recursively pi of ti. And then what you do, you sort the array. It doesn't really matter how you sort it. So for example, you could sort them lexicographically, like in the order they would appear in a lexicon. And once you have sorted them, you just do the same as you did before. You just put them together, you put a 0 in the front, a 1 at the end, and that's it. And it's easy to see two ordered trees are isomorphic if and only if, well, two rooted trees. Two rooted trees are isomorphic if and only if their encoding pi is the same. So how do you do that? How do you use that to solve isomorphism of trees? Well, the idea is try all roots. So you do something like this for all R1 in V1 and for all R2 in V2. If the encoding of your rooted tree T1R1 is the same as the encoding of your rooted tree T2R2, you return true. And if none of the roots work, you return false. You can see this gives you an O of n cubed algorithm, but of course this can be easily sped up by just not taking the first loop and just pick R1 arbitrarily, and it's easy to see that that also works, and it gives you O of n squared. There's actually a linear algorithm, which is a little bit, it's a little bit more clever. You have to look at the textbook. It's nicely explained in there. And it's a method where you can choose a canonical root. Like every tree has an obvious vertex that should be used as a root. And then you just choose these obvious vertices, and then you do your isomorphism for rooted trees. And this gives you a linear algorithm. All right, that's it for today. Thanks. Hello everybody. Last time I promised you that today we would talk a lot about walks and closed walks, and that's actually what we're gonna do. So last time I also showed you a picture of this beautiful national park, and today I show you a map. So this is the path map of this park. Here is the entrance gate, and when I visit this park, it is so beautiful I want to visit everything. And the nice thing about this park is actually to walk around it. So I want to walk around everywhere where I can, but I get easily bored, so I don't want to walk every path twice. So now let's see whether I can do that. So for example, if I start at the entrance gate, and I take a left here, and I go back, and I'm here, so where should I go? Well, of course, I mean, at some point I must do this, but then I'm back at the entrance gate, and I haven't seen the whole park. So I have to go back and I see things twice. So I made a mistake. That was not a good choice. So let's have another try. Let's look closer at the map and see what I should do. Well, if I start here, and then I don't turn left, but let's say I go straight. I go on to the summit. I enjoy the view. I hike down again. I'm getting hungry. So I go to the tree house to have lunch. I continue. Now I'm back where I was, but that's okay because only for a minute, and I continue here. I go like this, 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 and finally in the evening I go back to the entrance gate and I can go back to my hotel. All right, so in this map I was able to walk from the entrance gate, and in the end I arrived at the entrance gate and I visited every edge of this graph exactly once. So I did a closed walk that visits every edge exactly once. So this is called an Eulerian cycle, or an Eulerian walk, named after the famous Swiss mathematician Leonhard Euler from 18th century. And it is named by him because at this time, he solved a puzzle that was popular in 18th century Europe. So it is a puzzle it's a riddle about the city of Königsberg, which back then was located in Prussia, and nowadays it's called Kaliningrad and it's located in Russia. Well, actually the city didn't relocate, but the countries changed their borders. Anyway, this is not a history lesson. So as you can see here, there is a map of 18th century Königsberg. It has, there is a river, there is an island in the river, and there are several bridges. Actually, there are 7 bridges. 1, 2, 3, 4, 5, 6, 7 here. And the riddle is, maybe you stay here, here's your hotel, can you get up in the morning, make a tour that visits every bridge, and in the evening it brings you back to the hotel, but you visit every bridge exactly once. So we can actually formulate this as a problem in graph theory. We have these 4 vertices, we have these edges, so actually it's not a graph, but it's a multigraph, but never mind. And then we can actually forget about the rest of Königsberg and just focus on this graph. And now the question is there a closed walk that visits every vertex? So if there is, then it doesn't actually matter where we start. We could start anywhere. And if you try it, you quickly figure out it's not possible. And Euler gave a very simple reason why it's not possible. So look at this vertex here. Let's say your hotel is located there. So if you visit this bridge, you go out and at some point you enter this island again. So you have used two edges. Then you go out again and you come back. Now you have visited 4 edges. But now, no matter in which order you do, there will always be one bridge left that you haven't explored yet. Because this vertex has degree 5. And every time you leave it and you come back, you use 2 edges, and therefore you will never be able to visit all the edges. So this does not have an Eulerian walk, because it has an odd degree vertex. So here's the definition: an Eulerian cycle is a closed walk that visits every edge exactly once. And there are two obvious obstacles for a graph to have an Eulerian cycle. The first is, if G is disconnected, then obviously you don't have such a cycle, because you simply cannot get from one part to the other. And the other is, if G has an odd degree vertex, no matter, let's say you start here, you go out, you come in, somehow you go out, you come in, and in the end there will be at least one edge left that you cannot take. Okay, so these are two obvious obstacles. So if your graph is disconnected or it has an odd degree vertex, then your graph does not have an Eulerian cycle. And the cool thing is that there is a theorem that these are the only two obstacles, which means if a graph is connected and every vertex has even degree, then it has an Eulerian cycle. So this is called a characterization. You have an if and only statement. You have a condition that's necessary and sufficient. So now let's try to prove this theorem. As so often, we start with a definition. A partial Euler walk, let's abbreviate it as a PU. So a PU is a walk that visits every edge at most once. And this definition is good because it allows us to start with a partial Euler walk, maybe the empty walk where we just stay at the vertex, and then gradually enlarge our walk until we have a walk that visits all the edges. So now the strategy is grow the PU until it visits all vertices, until it visits all edges. So there are two cases. Case 1, your walk is not closed. So it could look like this. You start at U and you end at V. And it could look like this. You intersect yourself, you might go to V, you might go back, you might actually go back to U, but in the end you end up in V. So now note, this walk is in some way a subgraph of your original graph, and in this subgraph U has odd degree and V has odd degree, and every other vertex has even degree. So because in your original graph every vertex has even degree, it means there must be an edge that is incident to V that you haven't explored yet. So let's call this VW, and then let's just say you take your PU and you add the edge VW, and this is also a PU. So we managed to make it larger. Case 2. The PU is a closed walk. So we start at U and we go around, and at some point we end at U anymore. So don't be fooled. This might actually self-intersect. I just drew it as a cycle because it looks more nice. But don't be fooled. It could self-intersect. So keep this in mind. So there are again two cases. First of all, if this already explores every edge, then we are done, right? Otherwise, there is an edge that we haven't explored yet. And this edge could, for example, look like this. But then, of course, because our graph is connected, there is a path from this edge to u. So let's say there is a path from v to u, and at some point it must hit the cycle that we already have. It must hit the closed walk that we already have. And now it's of course obvious what we do. We just call this vertex x and we call it y, and then we can just start at w, we go to v, we go down to x, and now we can actually go all the way back to x. And this is basically now a larger pu. Of course, you have to be a little bit careful because it could be that actually your edge looks like this, but that's not a problem. In this case, you would also just start at w, go to v, and then go around in a circle. Or it could actually also be that you have an edge that looks like this, v, w and v. But also there, you can start at w, go to v, and then just go around the circle once, and still you have found a larger partial Eulerian walk. So this means as long as your walk doesn't explore all the edges, you can extend it. Because you take an edge that you haven't explored yet, there must be a path from your edge to your pu, because your graph is connected. So you do that, and then you go around and you have found a larger pu. And you iterate this as long as you can do, and in the end you will find a pu that explores all the edges, and this is your Eulerian walk. Okay? It's very simple. That's it for today. Thanks. Hello. Welcome back to our online course. Remember last time we talked about Eulerian cycles, and we proved that a graph has an Eulerian cycle, or I should rather say an Eulerian closed walk. Anyway, a graph has an Eulerian cycle if and only if it is connected and every vertex has even degree. And the theorem was not very difficult to prove. Today we are going to talk about something that it's almost the same. It's called a Hamilton cycle. A Hamilton cycle is a cycle in a graph that visits every vertex exactly once. So why should this be so radically different? Well, this is a surprising thing. It sounds very similar, but it is radically different. It is much more complex. So for example, when a non-computer science friend of mine asks me, what is complexity theory about, what is discrete math about, I tell them these two problems. And then I tell them they sound very similar, but one is super easy and the other is very, very different. It's very, very difficult. And today we're going to talk about this complex, more difficult problem, Hamilton paths and cycles. So you remember last time I took you to this beautiful park somewhere in nature, some national park. Today I want to take you to the suburbs of Beijing, the capital of China. So what you see here is a map of the so-called New Summer Palace in the northeast suburbs of Beijing. If you ever have a chance to go there, don't miss it. This is a beautiful park in a beautiful setting. I kind of made this map by myself, but that's kind of the way it looks. So in this park, you have a couple of lakes and a lot of green space, and of course, a lot of sites. Temples, pagodas, a marble boat, and everything. So if you pay the entrance fee, of course, you want to visit all the sites. For example, I just named 3 of the sites that you shouldn't miss. But let's say I go to the park, I enter at the east gate. My goal is to go there and to visit every site. So the site here are these little orange dots, little orange vertices. In the edges, these are just the paths where I can walk. So my goal is to find a cycle where I start at the east gate, and in the evening I come back to the east gate and I visit every vertex exactly once. So let's try. The This is not so easy, so maybe I fail. Okay, let's try. I start at the east gate, then I make my way up here, then I go maybe up here. I think this is called the long corridor or something. And now I have to be careful. Maybe I go up here. I go back a little bit. Now I go uphill to the big temple. I go to Suzhou Street. Maybe I have lunch there. I go back and I go downhill again. I go back to the lake. I visit the marble boat. And then I pass this bridge, and then now I'm on this narrow land bridge between the lakes, and now I'm home free because I can still go back. Here actually once I went there in, I think, early March or February, and I saw a guy winter swimming where there was still ice in the water. It was kind of impressive. Go to the small island and go back to the east gate, and then I go home. So here you have a path, you have a cycle that visits every vertex. Now let's try to do the same in the national park that we have visited last time. I start at the entrance gate, maybe I go here. So what should I do now? And now you see we run into a problem. So I want to visit this vertex and this vertex, so at some point I must cross over this edge. So there is no choice but to go here. But then I have to continue to here. And if I want to go back to the entrance gate without visiting any vertex twice, I have to go back. So here, it's not possible, as you can easily see. So here's the definition of a Hamilton cycle. It's just a cycle that contains every vertex. In other cases, it's a subgraph isomorphic to the cycle on n vertices. That's a Hamiltonian cycle or Hamilton cycle. Here are some examples. This is the graph of the dodecahedron, one of the 5 Platonic solids. Take your time and find the Hamilton cycle. I promise you there is one. And as a spoiler alert, if you can't find it but really want to find it, well, Wikipedia is always the answer. Anyway, so here you can find a Hamilton cycle. How about this graph? Let's try. Let's start at this vertex at the very top. And let's go around like this. Let's do this. And now I see I'm in a problem because I end up at a vertex where I can't go back. So this is not a Hamilton cycle, but here I have a subgraph that is isomorphic to the path of length n minus 1. So I have a path that visits all the vertices, but it doesn't end where I started. So this is called a Hamilton path. So you can try to find a Hamilton cycle in this graph, but as a warning, it does not have one. But you can try to figure out why it doesn't. Okay. So that's a Hamilton path. So remember last time we proved this beautiful theorem that a graph has an Eulerian cycles if and only if the 2 following conditions are met. It is connected and every vertex has even degree. So these conditions are obviously necessary, but the cool thing is they are also sufficient. So now what we want a theorem that says a graph has a Hamilton cycle if and only if some obviously necessary criterion is met and some other obviously necessary criterion is met. That would be really great if we could prove such a theorem, but unfortunately there probably is no such theorem. At least it's not known as we speak, and probably it does not exist. So here are some obviously necessary conditions. If G has a Hamilton cycle, then, well, it is connected. Every vertex has degree at least 2. Third, it doesn't look like this. Fourth, it doesn't look like this. By the way, such a thing is called a cut edge or a bridge. Right? An edge, if you take it out, it disconnects your graph. And this here is called a cut vertex. You can take it out and it disconnects your graph. So it doesn't have a bridge, it doesn't have a cut vertex, that's pretty obvious. But how about sufficient conditions? Well, actually what you should do, you should try to find more necessary conditions and see how far you get. What about sufficient conditions? Well, here is a theorem that is an example of a sufficient condition. It says if you take two vertices and they are not connected directly by an edge, if for all such vertices their total degree, if you add up the degrees, if this is at least n, then it has a Hamilton cycle. So for example, you have a vertex here, you have a vertex here that don't have an edge, but together they have many edges. So the sum is at least n. So degree of u plus degree v is at least n. So actually that tells you that they actually must have a common neighbor or something. Anyway, if this condition is met for every vertex, then it has a Hamilton cycle. That's Ore's theorem from 1960. That's what we are going to prove today. So, how can you prove this theorem? Well, let's simply try. You start with a vertex, you go on, and because maybe you always find an edge that leads you to a new vertex, but it could also be that at some point you get stuck. So it could be you end up at a vertex u, and all the edges, all the neighbors are somewhere on the path. Okay, it could look like this. And well, then we are stuck. There is no easy way to extend the path. So now, what can we do? Well, we can give names to these vertices. That's v1, that's vi, let's say vd. So d is the degree of u. Okay, so what can we do? Well, there is a case. Suppose this path is not yet a Hamilton path. So there is a vertex here, v, that is not in our path yet, and by assumption there is no edge between u and v. So therefore, the degree of u plus the degree of v is at least n. So, this probably tells you that v and u must have a common neighbor, but that doesn't really help you. What helps you is the following. You look at the path that we have already found, and you look at the successor of every of these vertices, and you call it w. So this would be wi, and this is wd. And now, this inequality tells you that v has large degree. It has degree at least n minus d. So it looks like this. This is v. It has a bunch of neighbors, and it has a bunch of non-neighbors. And this set here has size at most it has size at most n minus at most d. Well, actually v is a non-neighbor of itself, so I should kind of draw it differently. Let's see. So kind of we have a set here. That's a set of non-neighbors, and this has size at most d. And of course, it contains u. Right? Because by assumption u and v are not neighbors, so it contains u. So besides u, it contains d minus 1, at most d minus 1 vertices, which means it cannot contain all the w vertices, which means there is a w vertex somewhere in the neighborhood of v. So it means there is an edge from v to wi. Okay, and now this gives you a longer path. Now let's see, where is the longer path? So we start at v, we go here, then we go to u, we jump to vi, and we go all the way back where we started. And now this is a path whose length is one more than the path that we had. So we can always extend our path. Well, until we find a Hamilton path, then obviously we cannot extend it. So you see, in the end, we will find a Hamilton path. Let's say the last vertex is called n, and the first vertex is called 1. And there are two cases. Case 1, 1n is an edge. Well, this is easy because then you're done, right? Then this is your Hamilton cycle. But suppose there is no edge. Well, then there is the same game. Then we say, well, the degree of 1 must be at least n minus d. And then we do the same argument, but a little bit different. We simply, again, consider all the neighbors, vi, v1, vi until vd of n. And the neighbors to the right, w1, wi, wd. And by the same argument, n has a bunch of neighbors, and it has a bunch of non-neighbors. And this set has size at most d, so it contains n. So there is not enough space left for, well, wait, this is 1. This is 1, and it contains n. So there is not enough space left for all the w vertices, so one w vertex has to be outside. And we find an edge from 1 to some wi, and there is your cycle. Do you see it? Well, it's a little bit hidden. Yes, so we go from 1 until vi, we jump to n, we go back to wi, and we can go back to 1. And that's your Hamilton cycle. All right, this finishes the proof of Ohr's theorem. It's nice, right? Well, in the literature and textbooks, you usually don't come about Ohr's theorem, you come across a corollary of it, which is called Dirac's theorem. It's a little bit older, 8 years, and it says if every vertex has degree at least n over 2, then it has a Hamilton cycle. But this is, of course, a special case, because if every 2 non-neighboring vertices have total degree at least n, if every vertex has degree at least n over 2, then if you pick 2 vertices, the sum of their degrees is at least n. And then you can apply Ohr's theorem. But don't be fooled. This is a sufficient condition. It's not necessary. So for example, here you see a graph that obviously does not meet the condition of Dirac's theorem or of Ohr's theorem, but still it has a Hamilton cycle. So still we have a bunch of necessary conditions, we have a bunch of sufficient conditions, but we don't have a nice characterization that tells us a graph has a Hamilton cycle if and only if blah, 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 blah. Right? And this is probably inherent. There is probably no such criterion, because there is a huge theory within theoretical computer science that suggests that actually there is no efficient algorithm to find a Hamilton cycle if there exists one. And if you had such a criterion that tells you, well, if and only if, blah, 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 this would, in most cases, give you an efficient algorithm to find a Hamilton cycle. So therefore, most researchers believe this is really a complex problem and you cannot find an exact characterization. And with this note, I say goodbye for today. Hello everybody! As you know, as you might have noticed by now, this is an online course about discrete mathematics. It's not a class about algorithms. But this doesn't mean we cannot talk about something you might come across in an algorithms course. So in today's lecture, we will talk about spanning trees and minimum spanning trees. So this is actually a staple of an introductory algorithms class. However, it also makes a lot of sense to talk about it in discrete mathematics, and it will not be completely the same. So here we will focus a little bit more on the mathematical details and not so much on the implementation and algorithmic details. So let me first tell you what a spanning tree is. We have a graph here, and what do I have here? Well, it's a subgraph. Okay, it's not an induced subgraph, but it's a subgraph. It contains some of the vertices, some of the edges. Now this here is called a spanning subgraph because it contains all the vertices. So a subgraph that contains all the vertices, it's called a spanning subgraph. In the last example, here we see a spanning subgraph that also happens to be a tree. And this is called a spanning tree. So this lecture is all about spanning trees. Here is an example that I prepared for you. So this, as you can see, is a map of Europe. and I put a little dot for every capital of a country in the European Union. So, yeah, sorry for the Russians and the Ukrainians and so on, but in this example, In this example, I focus on the European Union. So let's consider the following scenario. By some miracle, the European Union has a lot of money, and for some reason, they don't want to spend it on, rescuing banks or financing agriculture or something. They want to spend it on building a high-speed internet across Europe. So as a first step, what they want to connect all the capitals of the member countries by a new technology, by a new high-speed internet technology. So here you see the 25 capitals of the European Union, and how can we connect them such that, how can we basically find a connected graph? Well, here's an example that probably is connected. I haven't actually checked. It is most likely not the most efficient way to do it. So what does efficient mean? Well, efficient means you somehow want to minimize the distances, because this new technology is expensive, so it probably makes no sense to make a direct link from Lisbon all the way in the west to Athens all the way in the east. That's kind of stupid. So you want to do something like this, that looks nice, that minimizes the sum of distances. So this problem here, it's called minimum spanning tree. You want to find a spanning tree of minimum cost. So here, the definition is as follows. We have a graph G and we have a cost function. So every edge has a cost. And we want to find a tree, for example, like this. And we are interested in the cost of the tree. The cost of the tree is simply the sum of the edge costs. And obviously, we want to find a tree that you want to find a spanning tree that minimizes the total cost. So how can we do that? Well, let's see. So one algorithm is the following. It's called Kruskal's algorithm. We take all the edges and we sort them from cheapest to most expensive, and we just insert them one by one if necessary. So for example, here, what is the cheapest edge? Well, this is the cheapest edge, so let's insert it. Then we have edge 1 here. Do we have another edge of cost 1? No, so we add edges of 2, like this. Okay, then we add this edge. But now we see this edge is actually not necessary, so we don't have to add it. But maybe we add this edge, we add this edge, this edge, this edge. But now we see we created a cycle, so we delete this edge, we don't insert it. We go through all edges of weight 2. And now we are done, I think. Are we done? I think we are done. And now we take the edges of weight 3. So, for example, these 3. This edge we don't take because it would create a cycle. This we don't take either. And that's the edges of weight 3. And then we take edges of weight 4. This obviously we don't take. This we don't take either. Here is an edge of weight 4, this we don't take either, and this we take. And now we are done. Okay, now we have found a spanning tree. Now the question is that the optimal spanning tree? Can we find something better? The answer is yes. It always finds the optimal spanning tree. And there is kind of several ways to prove that. I show you the most flexible. It's kind of, for me, my personal opinion, the most accessible proof, and it's also the most flexible. So the definition goes as follows. A set is good if there is a minimum spanning tree that contains it. So let's make an example. The empty set is good, right? Because it's contained in every spanning tree. If X is good, then of course X is acyclic. And if X is a subset of X prime is a subset of X, then X prime is also good. Okay. And our goal is the following. We start with the empty set, right? And then we add an edge in every step if it doesn't create a cycle. So we have to show if at any moment we have a good set, then the set in the next step where we add an edge will also be good. So in the end, we'll have a tree which consists of a set of good edges, of a good set of edges, And this means it's a minimum spanning tree because it's contained in a minimum spanning tree, so it must be a minimum spanning tree. So we have to show the following. We have to show the following cut lemma. I let you read through it for a while, and then I show it to you on an example. All right. So basically what it means is here we have a good set of edges, and it's not connected, so we can partition it into two parts. Like this, for example. And now there are several edges crossing it. Maybe here is an edge, maybe here is an edge, maybe this is an edge, maybe this. And now the lemma says, of all these edges, take the one of minimum cost, like this, and then I take this edge and I insert it, so let's say I make it red, and then x plus e is good too. That's what the lemma says. And if you think about it, this will actually show you that the algorithm is correct, because the algorithm in every step takes the cheapest edge that connects two connected components. So obviously Kruskal's algorithm satisfies the condition of this cut lemma. So your edge set stays good all the time, and in the end you end up with a good set, so you have a minimum spanning tree. So now it suffices to prove the cut lemma. Okay. Let's try to prove it. So first of all, let's take a partition into two sets. This is S. This is S bar. And now let's take the edge that is cheapest and goes from S to S bar. Let's say this is this edge. This is E. Okay, so what do we know? Well, X is good. So X is contained in some minimum spanning tree. So case 1, if our set E is an X, E is of course not an X. If E is in T, then we are done, because then obviously X plus E is also contained in T. Second, if not, then we do the following. We consider T and we add the edge E. And because now this has n edges, it must have a cycle. It has a cycle containing E. So the cycle looks somehow like this, contains E. But because it is a cycle, at some point it must cross the cut again. So let's say this edge up here is called F. It might actually cross it several times, but at least once, right? It crosses it at E and at least some other time. In this edge where it crosses it the second time, let's call this edge F. So we know that the weight of F is at least the weight of E, because the weight of E was chosen to be the cheapest edge that crosses the cut. And now you define T prime to be the following. We take T, we add E, which creates a cycle, and we remove F. And now you have to convince yourself that this is again a tree. Well, how could you convince yourself of it? Well, it has n-1 edges. Is it connected? Well, maybe, but it surely is acyclic, right? Because adding E creates one cycle, and then we remove an edge from this cycle, so it breaks the cycle. So it's acyclic, and by the tree theorem that we have proved a couple of lessons ago, it must again be a tree. Okay, so what is the cost of T? The cost of T is just the cost, well actually I think I used C instead of W, cost instead of weight. So let's be consistent, C of F. Okay, C of T prime is C of T plus C of E minus C of F. And because C of F is larger than C of E, at least as large, this is at most C of T. But T is a minimum spanning tree, so actually C of T prime must be equal to C of T. So T prime is also a minimum spanning tree, and it contains the set X plus E. So we see X together with E is contained in the edge set of T prime, and therefore it's good too. So that proves the theorem. It proves the cut lemma, and it also proves the correctness of our algorithm. And notice the beauty of the cut lemma, it gives us a lot of flexibility, so we can come up with other algorithms that work differently from Kruskal's algorithm, and by the cut lemma we also see that they are correct. So let's go back a little bit to our example, and I show you something that's called Prim's algorithm. You start with a vertex in the empty set. And now you take the cut, where this is S and the rest is S bar. So what is the cheapest edge? This. Okay, so the cut lemma says we can actually add this edge. Now we have this set. And now these are two connected components, right? This is one connected component, so this is a cut. And now we choose the cheapest edge that goes out. So let's say this edge. By the cut lemma, it's still a good set, so we're on the right track. Then we let this be S, and we choose a cheapest edge going out, like this. And if we, we continue until we find a tree, until everything is connected. Okay, that's called Prim's algorithm, and again, by the cut lemma, it is correct. It gives you a minimum spanning tree. But you can also come up with different algorithms. Now you could say, well, you want S to be this, and this here is S bar. And you take the cheapest edge crossing the cut, there would be this edge. And your algorithm adds this. I don't know whether it would make sense. I don't know whether this would be faster in any way or more efficient than Prim's or Kruskal's algorithm, but the cut lemma allows you to do that. It gives you a lot of flexibility. All right, so today we have seen minimum spanning trees. We have seen two algorithms for finding a minimum spanning tree, and we have thoroughly proved why these algorithms are correct. All right, I think that's enough for today. Thanks. Hello everybody, welcome to our online course on discrete mathematics. In today's lecture I will show you an especially exciting example of combinatorial counting. This is something called Cayley's formula. It's a formula that tells you how many trees you can find on n vertices. So as an example, let's put here 3 vertices. Let's put here 4 vertices. This is a tree. For example, note that our vertices are numbered 1 to n, so this tree here actually is a different tree from the one to the left. These are different trees. All right, so for example, for n equals 3, how many trees can we get? Well, we get this tree, and then we get this tree, and then we get this tree. So for n equals 3, we get that T3 equals 3. Right, for 4 vertices, this is an exercise that I encourage you to do. I want to jump right into the example of 5 vertices, because now it gets a little bit challenging. So what would be a sensible way to count the trees? So, a special kind of tree is a path, right? So paths. How many paths do we have? Well, the thing is, if I put a little arrow here, then a path is just an ordering of the n elements, so I get 5 factorial many. But by this method I get every path twice, because I get once in this direction and once in this direction. And we just take this and divide it by 2, so we get 60. There are 60 paths. Okay. So another kind of special tree is the so-called star. Star is something we have one vertex and then it just has an edge to every other vertex. How many stars do we have? Well, you see, as soon as I tell you what the center is, you know what star I am talking about. So there are 5 stars. Okay, there is some other tree that is left, which is this. A tree like this is neither a path nor a star. So what can we give it a name? So if we rearrange the vertices, it would look like this. So this would be 4, this is 1, this is 5, this is 2, and this is 3. Let's call it the T shape. So how many T-shapes do we have? Well, it's a little bit tricky to count, but let me tell you. If I tell you which vertex this is, the red vertex, and if I tell you that the blue vertex here is vertex number 2, and the green vertex is vertex number 3, well, then you already know which T-shape I'm talking about. So I can identify them by telling you the red, the blue, and the green vertex. And you can see this is 5 times 4 times 3, which is also 60. If we sum it up, we get 125. Okay, so T5 is 125. How about 6? Well, here it gets a bit nasty, so I prepared some computer slides. Again, we have 6 stars. How many paths do we have? Well, we have 6 factorial over 2 paths. This is 360. And then we have like weird shapes. Like this, for example, it looks a little bit like T-shape, but how should I call it? Well, I call it the Scandinavian cross. Because you see here, I put it like this, and it looks a little bit like the flag of Sweden, Denmark, and Norway. So how many Scandinavian crosses do we have? Well, again, if I tell you what the blue, the red, and the green vertex is in the Scandinavian cross, then you know which one I'm talking about. So this is 120. And then we have trees like this. I call this the Star Wars spaceship. And this is kind of tricky to count. Well, if I tell you the set of blue vertices and the set of red vertices, then you can identify the tree. So I have 90 choices here. This is, by the way, this is by no means trivial. It's easy to make mistakes here. But I really double and triple checked it. Then this graph I call the euro symbol. And this is especially tricky to count, so I have to tell you the blue vertex, the set of red vertices, and then the green and the violet vertex. So you can see this, I can identify by this, and this gives 360 euro symbols. And lastly, I have the Y shape, of which we also have 360. So this was fast. Go through it again, convince yourself that this was a correct calculation. If we add up everything, we get 1,296. Okay? So this is so much fun. Let's continue with 7. Actually, let's not do that, because I think for 7 there's just no way to do that within one lecture, and it quickly gets extremely complicated. So this way seems hopeless. You know, by just enumerating all the trees and looking how can they look, it's impossible to determine the total number of trees. But you know, anyway, let's summarize what we have so far. So we have seen this table. On 5 vertices we have 125, and on 6 we have this, and the rest you do by yourself. It's not too difficult. And you see that this is, wait, let's go back. You see that this is actually 6 to the 4, this is 5 to the 3, this is 4 to the 2, this is 3 to the 1, and this is 2 to the 0. So this, of course, suggests the following conjecture, that the number of trees is n to the n minus 2. Okay, so n to the n minus 2, this is the number of trees on n vertices. How can we prove that? Well, if we look at it, n to the n, what is n to the n? Well, we have seen such a thing before. N to the n, this is the number of functions from v to v. So maybe we can identify functions and trees. So here's the thing. If you have a function from v to itself, you can draw arrows between. So for example, this function, I make an arrow from 1 to 2, from 2 to 8, from 3 to 8, from 4 to 5, from 5 to 2, and from 6 to 5, from 7 to 8, and from 8 to 1. So if I put it a little bit more nicely, it looks like this. I have 8, 1, and 2, 8 points to 1, 1 points to 2, and 2 points back to 8. And then I have the 7 that points into here, and I have the 5 pointing into the 2, the 4 pointing into the 5, and well, also the 3 pointing into the 8, and 6 pointing into here. So this almost looks like a tree, right? Not quite, but it almost looks like a tree. So maybe we can, by some clever way, identify functions in trees. So for this, we actually need a definition. Here's a tree on 20 vertices. And now what I do, I identify one vertex as the head and another vertex, let's say back this, as the butt. So formally, here's the definition. If you have a tree, a head, and a butt, then this triple is called a vertebrate. So why is it called a vertebrate? Because, with a lot of fantasy, it actually looks like the skeleton of a vertebrate, right? So here you have the head, here you have the butt, and the rest, it is actually kind of a tree, right? So that's why it's called a vertebrate. All right, so let Sn be the number of vertebrates on n vertices. And it's easy to see that Sn equals Tn times n squared, right? Why? How do we get a vertebrate? Well, we take a tree and then we select one point to be the head and one point to be the butt. So this is n squared choices we can make. So we want to prove that Tn equals n to the n minus 2. So now what we actually do, we show that Sn equals n to the n. So we want to show that the number of vertebrates is n to the n. How do we do that? Well, I will show you how to take a vertebrate and transform it into a function from v to v. And then I will show you that this process is invertible. You can again take the function and get back the same vertebrate. So in other words, we will construct a bijection between the vertebrates and the functions. And this will show us that their number must actually be the same. So how do we do that? Here we have a vertebrate. Actually, we have a tree. So let's make it a vertebrate. Let's choose a head and a butt. And then let's take the path, the unique path from the head to the butt, and let's call it the spine. Right? So if you have a vertebrate and then the path from the head back here, this is called the spine of a vertebrate. And let's write down the spine. So the vertices on the spine are 1, 10, 13, 15, 4, 7, 6. Okay, so now let's again write the vertices, but in a sorted way. 1, 4, 6, 7, 10, 13, 15. So what is this? This is a function from the spine to the spine. And this will be our function f. So let's write it down in this arrow notation. 1 maps to itself, 4 maps to 10, and 10 maps back to 4. And then we have 6, 13, 7, 15. Like this. And now what do we do with the rest of our vertices? For example, where do we map 20? Well, now it suggests itself. 20 is a neighbor of 1, so of course we map it to 1. And the same with 14 and 9. And 3 is a neighbor of 10, so we map it to 10. And 11 is a neighbor of 3, so we map it to 3. Right? So the rest of the function will just look exactly like the tree. I don't continue here, you can do it yourself. So basically, you take the spine defines a permutation into itself, that's your function, and for the rest, what is attached to the spine, well, you just map it towards the spine, and that's your function f. Okay, now I want to show you that this process is actually invertible. So if you give me a function f from v to v, I can construct a vertebrate out of it. Let's do that. This is our function. So first, let's identify what should be the spine of the vertebrate. Well, it should be everything that lies on a cycle in our function. So this here. So we see 1, 8, 2, the other way around, 1, 2, 8, no, like this, 1 to 8, 1 maps to 8, 2 maps to 1, and 8 maps to 2. Okay, that's your function. Well, that's x, and that's f of x. And this already identifies the head and the butt. So the spine looks like this, 8, 1, 2. So this is the butt and this is the head. And now 5 maps to 8, which means in the vertebrate it's just a neighbor of 8. And here you can construct your tree. So here, this is the vertebrate. So I have shown you how to take a function and again translate it into a vertebrate. So here's the summary. A vertebrate is this triple, and we have shown that there are Tn times n squared vertebrates, and then we have shown this one-to-one correspondence between vertebrates and functions, which told us that there are n to the n vertebrates, and from this we derive Cayley's formula, which is the number of trees on n vertices is exactly n to the n minus 2. Thank you for today. Hello everybody! I was looking forward very much to today because today's lecture and the next is my favorite in the whole course. You remember in the very first lecture I showed you an example about network flows, about these transportation networks where you have a start and a target and you want to transport some goods from left to right. So these goods could be data in a computer network, it could be trains or whatever trains transport in a rail network, it could be oil in a network of pipelines where you want to transport as much as you can from an oil well to the oil refinery. It really doesn't matter from the viewpoint of discrete math, it's simply a graph with two vertices, the start and the target. So here, for example, we route one unit of flow. Flow is whatever commodity we are talking about along this red path. Then we have the blue path, we have the green path, and note that the green and the red path intersect, but this is fine because what restricts the capacity of the network are not the nodes, but the links. So the edges are restricted in capacity. This is what we define to be the capacity of a network. It is the maximum number of independent paths from S to T. So now if you want to sabotage the network, you can place these little bombs on these four edges, and if you destroy these edges, you have successfully disconnected it. So now you cannot go from start to target anymore. This is what we define to be the vulnerability. It's the minimum number of edges you have to remove in order to disconnect the network. And it's pretty obvious that the capacity is at most the vulnerability. In this specific network, you can change the green path, you can change it, and you make space for yet another path. And now you see here in this network, the capacity and the vulnerability are actually the same number, in this case 4. And this turns out to hold in general. That's known as the Max-Flow-Min-Cut theorem. And today I want to introduce network flows and cuts in general, and then in the next session we are going to prove this very nice theorem. Okay. In general, the setup is a little bit more complex, but with what we have seen now in graphs, it's actually not very difficult. So the first thing is we actually have directed edges. So it could be that you can transport something from A to B, but not back, okay, like one-way roads. The other thing is not all links have the same capacity. It could be that some links have capacity 4, some have capacity 1, and so on. So in general, a flow network is a directed graph together with a source vertex and a sink vertex T and edge capacities. These are the black numbers next to every edge. Now, if we have these edge capacities, we can actually generalize and say C is actually a function from V times V into R, where we just define C of UV to be 0 whenever UV is not an edge. Conversely, if you give me a function from V to V into R, a capacity function, I can just say, well, E is the support of it. So E is the set of all UV that have positive capacity. It is sometimes easier to think of C as a function from V times V and not as a function on edges. Okay. So here is an example of a flow. There is a path, and here is a path, here is another path, and I could route 1 unit of flow through the blue path and 0.5 units of flow through the red path. So this is possible, right? I can of course also choose this. I can split the blue flow into 0.1 and 0.9, and then you see along these edges you have 0.6 flow. So actually we can forget about colors and we can just say, well, whatever enters this vertex has to leave it, but we don't really care which part of the oil goes here and which goes here. It's just the inflow has to be the outflow. Okay, so we can forget about these colors. At this point, I think we should formally define what a flow is. So now I think the concept of a flow deserves a proper mathematical definition. So if you have a flow network G STC, a flow is a function from pairs of vertices into real numbers that satisfies the following constraint. First of all, it should never exceed the capacity, obviously. This is called the capacity constraint. Second, whatever flows into vertex V has to flow out of vertex V. There is no flow that is lost at V and nothing is generated at V, right? Okay, so this equality has to hold for all vertices except the source and the sink. However, it turns out for a mathematical treatment, it pays off to reformulate this constraint as follows. So first of all, we introduce something that's called skew symmetry. We say the flow from U to V is the negative value of the flow from V to U. So whenever we have a flow from U to V, let's say we have 4 units of flow, then we define the flow from V to U as -4. Okay? This might strike you as odd, but it's actually a convention that is also used when people study electricity networks, like how current flows between certain points. And it just makes the treatment much easier. So now, for example, we can reformulate flow conservation as follows. The total outflow at V should sum up to 0. Right, that's the definition of a flow. And the value of a flow, which is what we want to maximize, is the outflow at S. Actually, here is a typo. Oh my god. It's the flow S to V. Okay, that's the value of a flow. Okay, so let me give you some examples of a flow. Here is one. There are weird things happening. So here, for example, there is something running in circles. Or here you see there is something flowing back into the sink. Again, you might think this is weird, but if you look at our definition, this is perfectly allowed. What I show here is a flow. Also, you might have something like this. So here, stuff is also flowing out of the sink back into the network. Again, this is a flow because it satisfies all our conditions in our definition. So here in this flow, let's see, what is the network? What is the value of this flow? Well, you see here, there is 1 unit flowing out here and 0.5 flowing out here. So 1.5 is flowing out of the sink. And here it's 0.9 and 0.6. So 1.5 units are flowing into T. So these are the same values, which is almost obvious, right? Whatever flows out of the source has to flow into the sink, because nothing can get lost in the middle of the network and nothing can be generated. So we have this following lemma. It's almost obvious, but let's try to prove it formally. Proof goes as follows. Let us sum up the flow over all pairs of vertices. On the one side, I can say, well, this is minus Vu. Now we can actually exchange the order of summation, and we see that this here is actually the same as this. So you have a number that equals its negative part, therefore it must be 0. On the other hand, we can split the sum by saying, well, u, the vertex u could be s, it could be t, or it could be something else. And then we get this. So here we sum over all remaining vertices in V without S and T. But now you see this term here, this sum is the total outflow at vertex U, and by flow conservation, it's 0. So only the two first sums survive, and I can rewrite the second sum by skew symmetry, and I get the following. So now you see this here is the outflow at the source, this is the inflow at the sink, and their difference is 0. This finishes the proof. Cool. Again, here we have a flow. It's not the best flow. And let's ask our question, how can we prove upper bounds? Let's say, how large can, in theory, we make our flow? So note that all the flow must go through one of these edges. Therefore, it seems obvious that the flow cannot be larger than this, which is 10. Alternatively, I could choose this large set. And now you see all the flow has to pass through one of these edges. And therefore, it cannot be larger than 2 plus 1 plus this, which is 7. So this method gives us, this is a tool how to prove upper bounds on the value of a flow. And again, this is very important, so let's come up with a mathematical definition. This is called a cut. So a cut, or more specifically an ST cut, is a set of vertices that contains S but not T. And the capacity is defined to be the total capacity of edges crossing this cut. So we have a set S here, we have V minus S here, T is over here, S is over here. And if you sum up all the capacities, you get this. And if you sum up all the flow, you get this. You must be careful with flow, because if something is flowing back, let's say if 4 units of flow are flowing back, then actually this counts as minus 4 units of flow flowing forward. So you have to take this into account as well. All right, so this is the capacity of S and F of S. So here is the lemma. It says the value of a flow is at most the capacity of S. And this is basically also what we have seen in the beginning. It says that the capacity of a network is at most the vulnerability. So the capacity of S here is a generalization of our concept of vulnerability. How do you prove this lemma? First of all, the value of F is everything that flows out of S. And this equals everything that flows out of capital S. And I don't prove this, that's an exercise for you. The proof is very similar to the summation we had a couple of slides ago. But if you have this, then you see this sum can be at most the sum of the capacities by capacity constraint. And there you have it. The value of the flow is at most the capacity of the cut. Okay? And here is a surprising theorem. It says there is a flow and a cut such that these values match. And then this must be a flow of maximum value, that's called a max flow. And this must be a cut of minimum capacity, it's called a min cut. So the theorem tells you that a max flow equals the min cut. These two numbers coincide. They are the same. So this is the famous max flow min cut theorem. And in the next session, we are going to prove that. For today, we are done. Thanks. Hello everybody! Today, as promised, we will prove the max flow min cut theorem. As a reminder, last time we defined what a flow network is and what a flow is. So a flow is a function satisfying certain constraints, the capacity constraints, skew symmetry, and flow conservation. And we also defined cuts, which are best pictorially drawn like this. The capacity of a cut is the total capacity of the edges crossing it. We have proved the lemma that the value of a flow can never be larger than the value of any cut. And today we are going to prove that there is a flow and a cut such that these two values actually coincide. As a preparation, let's look at this very simple flow network. We can find a path from S to T and route one unit of flow through it. After we've done it, let's pause for a moment and think what is left of our capacities. So you can, for example, see here this edge has capacity 2 and we used 1 unit. So there should be 1 unit left. Here we used 1 unit, so nothing should be left, and so on. So this depicts what remains. Alright, so in this network you see there is no path left from S to T. So does that mean we have found the optimum? No, not really, because we can do something that is slightly weird, but actually we can do it. We can start from S, go through here, 1 unit of flow, but now instead of going here, which we can't because this edge is already used, we can push back flow, unuse this edge, so to say, and continue around here. If this is confusing, don't despair, we will make everything formal in a minute. Basically what it tells us, whenever we route flow here, we can use the edge in the backwards direction in the next step. So actually, the remaining capacities should look like this. We don't only have the green edges, we also have these brown back edges. And in this network, let's stick to our convention that if something has 0 capacity, then it's not an edge anymore. So this network should look like this. Okay. So now in this network, we can find another path like this and route 1 unit of flow. So let's try to combine this. We have 1 unit of flow here and 1 unit of flow like here. And now let's see how this combines to a flow. Well, this gives us 1 unit, 1, 1, 1. And this gives us 1, 1, 1. Now we have to be careful because actually we are sending flow in the other direction. So we should put a -1 here, 1, 1. And altogether you can see that this gives us a flow, and the flow kind of looks like this. 1 unit here, 1 unit here. So this business of inserting the edges going back might strike you as weird and unusual. So let's try to formally define it and see that it makes sense. So if you have a flow network and a flow, we define the residual capacities as follows. Cf is C minus F. So remember, what is C and F? C and F are functions from V times V into R, which means we can subtract and add them as functions, right? And if we take C minus F as a function, we get a new function, which we call Cf, and this is the residual capacity. And here is the core lemma. If you have a flow in G, and now you have a flow F prime in GF, then you can combine them and get a flow in G. That's what he did on the slide before, and now we are going to prove that this works in general. So what we have to do is we have to check that this new function, f plus f prime, satisfies our constraints of a flow. It fits our definition of a flow. So first, we have to show the capacity constraint. We have to show that this is at most C. And indeed, f prime is a flow in GF. So it respects the capacity constraints and it is at most CF. By definition, CF is C minus F, and it nicely cancels out, and here you get it. Our flow respects the capacity constraints. Second, we have to show skew symmetry. But this is really a simple exercise, so I'll let you do it. And third, we have to show flow conservation. So if you take a vertex V and you sum up this value, you can actually tear this sum into two parts. And this part. And we see, because f and f prime are both flows, this is 0 plus 0. So flow conservation also holds for the combined flow, right? Okay, now you see the way we defined flows actually made it super simple to prove this lemma. So again here, let's practice this definition. We have a network, we have a flow. Here is our residual network. Good, so now we are ready to prove the max flow min cut theorem. So what we do, we choose a max flow F. We just, suppose we have it. And actually, I should warn you, I'm cheating just a little bit, because I gentlemanly assume that there is a maximum flow. But this is not completely obvious. Right? I should prove to you the existence of a maximum flow. It could be that it goes on and on and on and on. You find larger flows, but it doesn't reach this limit or something. So I would, technically speaking, I'm cheating you here a little bit. However, for an important special case, we will see a proof of this at the end of today's lecture. For now, never mind. Let's just assume F is a maximum flow. So second, let's consider the residual network. I claim that this network has no path from S to T. And indeed, if it did, we could take such a path And remember our convention, every edge has positive capacity, otherwise it's not an edge. So now we have this path and we can just route a small amount of additional flow and we would get a larger flow. So we could choose a flow Fp along this path and then F plus Fp would be larger than the value of F, which is a contradiction because we assume that F is a max flow. Okay, so there is no path, so it looks like this. We can define S to be the set of vertices V such that there exists a path from S to V in GF and by point 2 we know that T is not an S. But obviously little s is in capital S. So what does this tell us? It tells us that S is a cut. Also, if U is in S and V is in V minus S, then we know that the residual capacity of UV is 0. Why? Well, because there is a path from S to U. If we had the edge from U to V, then there would be a path from S to V too, right? So by definition of S, there is no residual capacity crossing this cut. And now the proof basically finishes itself. The value of F, as we have seen, as you have proved in an exercise, is this sum. But now you see, because CF equals C minus F, we have that CUV minus FUV equals 0 for all such vertices. So the capacity equals the flow for all these edges crossing the cut. And therefore we get the following equality, and this is simply the capacity of the cut S. And there you have it. We have a flow. There it is. All right. We have a flow F and we have a cut S, and the value of the flow matches the capacity of S. So the crucial observation is that for all these edges here, the residual capacity is 0, and this means the capacity, the original capacity, must actually equal the flow F, right? So here you have it. And this finishes the proof. But it does a little bit more. It also suggests an algorithm how to find a maximum flow. So for example, what you could do, as long as you find a path, you take a path and you route as much flow as you can through this path. And then you take the residual network, you again find a path, and so on and so on. And if this ends, then there is no path left, and you can define the set S as we just did before, and then F is a max flow and S is a min cut. All right? So this algorithm, if it terminates, it returns a max flow and a min cut. Now, if we can prove that this algorithm terminates, we have also proved that there is a maximum flow. I should say this algorithm is called the Ford-Fulkerson method. And if we assume the following, if C of UV is an integer for every edge, then whenever we find a path, we can route at least one unit of flow. So the value of the flow increases by 1 in every iteration, which means it must at some point terminate, because it cannot go to infinity, because everything is finite. So for integer capacities, everything is fine. The algorithm terminates, it proves that there is a max flow, and it returns a max flow and a min cut. However, if our capacities are real numbers, it's not that simple. Actually, there are examples where this algorithm does not even terminate. So we have to fix it, and the fix is quite simple. We choose this path here wisely. Choose P to be a shortest SP path. And with this fix, it's known as the Edmonds-Karp algorithm. And you can show that it has at most n times m iterations. So here n is the number of vertices and m is the number of edges. And every iteration requires that we find a shortest path, which we can do in linear time, for example by breadth-first search. So this gives us an n times m squared algorithm. But proving the theorem actually is slightly nasty, so we're not going to do it in this course. And actually, if this was an algorithms course, we could continue for the next 3 weeks just talking about algorithms for maximum flow, making it more and more efficient. But we are not an algorithms course, we are a discrete math course, so we are not going to do that. Instead, we are going to talk about applications of this beautiful theorem. So here is an application that becomes clear if you see this algorithm. If all your capacities are integral, then this algorithm will return a max flow. But even more, the max flow will have integer values on all pairs, right? Because every time you find a path, you add at least one unit, you add an integer amount of flow. So in the end, the flow will only contain integer values. And this is a very important observation that we are going to use next time. All right, I'm done for today. I hope you enjoyed it, and I see you next time. Thanks. Hello everybody, and welcome back to our course on Discrete Mathematics. Today I want to introduce you to an important concept of graph theory. The one is bipartite graphs, the other is matchings in graphs. But first of all, let me make a small announcement. Believe it or not, today is the first time in my whole life that I'm giving a PowerPoint presentation. Now this sounds ridiculous, but that's how it is. So believe it or not, so far I have been using a wonderful program called IPE, to produce the beautiful PDF slides of this course. And then when I was done with the PDFs, I used this Surface Pro and the program called Drawboard to actually give the presentations and write into the PDF in a live fashion. And everything went perfect until today, where for some reason Drawboard installed an update. And now it's unusable for presentation purposes. And somehow I cannot downgrade to the previous version, so we just spent like 2 hours figuring out what to do. Finally, we decided to convert the whole PDF into PowerPoint. Somehow we were able to do this, and it worked kind of okay. It actually looked still quite nice. So I'm very impressed. And this is why I'm today giving the first PowerPoint presentation of my life. Welcome to all of you. Let's start with matchings in bipartite graphs. As a motivating example, suppose you have to organize a 3-day workshop, Monday, Tuesday, and Wednesday. And for this workshop, you invite 5 keynote speakers, Dr. A, Professor B, C, D, and E. And you want each of these keynote speakers to give a keynote talk, keynote speech, at one of the 6 available time slots. Now, of course, the speakers are very busy people, so they don't have time all the time. For example, Dr. A only has time Monday and Tuesday morning, and so on. So now our job is to find an assignment from keynote speakers to available time slots that fits everybody. So let's try it to see whether we can do something meaningful here. For example, I can tell Professor D to take the Wednesday morning slot. This is kind of a safe choice because he's the only one who has time Wednesday morning. And by a similar reasoning, now here, Professor B can take this slot, Dr. A takes this, and so on. All right. Okay, so everybody is happy. Every speaker has a time slot. Has a preferred time slot. It's okay. But now let's look at a second example and try to figure out what we can do here. So for example, we can again say Professor E should talk Wednesday morning. Professor C should talk Tuesday morning. There is no harm in doing so. There are no conflicts. But now we run into trouble because we have 3 remaining unassigned speakers and they only have time at 2 time slots, namely Monday morning and Tuesday afternoon. So you see here there is a mismatch. There are still 3 unassigned speakers and they only have time at 2 different time slots. So in this example, no matter what you try, we are not able to assign our speakers to available time slots. All right? So I think now we are ready for some formal setup. The key notion here is the one of a bipartite graph. A bipartite graph is simply a graph, vertex set and edges, but the vertex set comes partitioned into a left set that we call U and a right set that we call V, and edges only are allowed to be between these 2 sets, not within one. So this is a bipartite graph. Now in a bipartite graph, a matching, something like this, it's a set M of edges that do not touch each other. So they don't share any endpoints. That's a matching. What's more, if you look at a set here, for example this, a set A, for a set A in U on the left-hand side, we define gamma of A to be the neighborhood. The neighborhood, meaning all the vertices on the right-hand side that are adjacent to the vertices in A. So here the neighborhood would consist of these 2 vertices, that's gamma of A. And then we define the discrepancy of A, delta of A, to be the size of A minus gamma of A. That's the discrepancy. So the discrepancy of this set here would be 1, because A has 3 elements and gamma of A has 2 elements. And now you see that's exactly the argument we used before, that we don't find a perfect assignment. So now you see every matching must leave at least delta A vertices of A unassigned, because there is simply not enough space to assign it to. Let me give you one more example. So another set, for example, let's say A is just a set containing this vertex, and then what would the neighborhood be? Gamma of this vertex would consist of these 4 vertices, and then the discrepancy is actually negative. Discrepancy would be minus 3. So we define the discrepancy of the graph to be the maximum over all delta A for all A on the left-hand side over all sets. And now you see some sets can have negative discrepancy, but the maximum discrepancy of the whole graph will always be 0 or more, because we can choose the empty set here, and then the neighborhood of the empty set is also the empty set, and the discrepancy is 0 minus 0, which is 0. So the maximum discrepancy, delta of G, is always a non-negative number. All right, here are all these definitions, again, a little bit more nicely written for further reference. Now, what I informally told you before is something that I like to call Hall's theorem, the easy part. It says if you have a set A on the left side and you have a matching, then the matching cannot be bigger than U minus delta A. In other words, the matching must leave at least delta A vertices unmatched. And well, this is easy to see, but what's not easy to see and not easy to prove is the other part, which I call the hard part of Hall's theorem. It says there is actually a matching and a set where these two numbers match. This is called the hard part of Hall's theorem. So altogether you can combine these two things into something that's called Hall's theorem. If G is a bipartite graph, then the maximum matching has size U minus delta G. So this is an example of a theorem where something that's obviously necessary is actually also sufficient. And we will prove Hall's theorem in the next session. We don't have time today, but what I want to do today is I want to talk about algorithms. So in the beginning, I gave you a bipartite graph that had a total of 11 nodes, I think, were like 5 keynote speakers and 6 time slots. And this was reasonably small, so we could figure out by hand that the best thing we could do was to assign 4 speakers to a time slot, but we couldn't assign all 5 speakers to a time slot. But if you have a very large bipartite graph, well, then we need a clever algorithm to do that. And this is what I'm showing you now. I'm going to show you an efficient polynomial time algorithm for maximum matching. And the cool thing is we actually don't have to do a lot of work because we can recycle an algorithm that we have seen in the last sessions. I'm talking about maximum flow. So here's what you do. Here's your bipartite graph. I add 2 vertices. I add a source vertex S and a sink vertex T. And I want to take this bipartite graph and make it into a flow network somehow such that I can apply the maximum flow algorithm. So I do something like this and like this. So I give every edge a direction and I add edges from S to the left side and so on. To make this a flow network, I have to tell you what the capacities are. Capacities are this. Like in the middle, they have infinite capacity. But now you should shout at me and say, well, last time in the last sessions you said the capacity is a real number, but infinity is not a real number. You're right. So if you don't like this infinity, down here what you could do, you could replace it something like by 2 times u, where u is the number of vertices on the left side. But conceptually, you will see everything works fine, but conceptually it's easier to think about this capacity as really being infinity. Good, so now we have a flow network and we can find a flow here. And now we have to think, what does the flow have to do with a matching? One direction is kind of easy. Suppose I give you a matching in the bipartite graph. We can extend this matching to a flow in the network. So we start with a matching of size 3 and we extend it to a flow of value 3. Now the question is, can we invert this? If I give you a flow, can you give me a matching of the same size? Well, it seems obvious, right? I mean, here we have a flow of value 3, and we just go back, and here's your matching of size 3. Fair enough, but how about a flow like this? This is also a flow of value 3, but can you transform it easily into a matching? Well, now it's more difficult, and it is more difficult because your flow values here in the middle aren't integers. If everything were 0 and 1, it would be easy, right? But here we have a flow of 1/2. It's not clear how to extract a matching from this. Luckily, we remember from the session about maximum flow that we proved the following theorem. There is a maximum flow that is integral. If all the capacities in our network are integers, then there is a maximum flow in which every flow is integer. For example, like this. And if you study this network, it's easy to see that the flow can only be 0 or 1. So every edge that carries flow has to carry 1 unit of flow. And given such an integral flow, it's actually easy to extract the matching. And now you see, if you take a maximum integral flow, it must be a maximum matching. So the total algorithm looks like this. You start with a bipartite graph, you make it into a flow network, you find an integral maximum flow in this network, and then you extract your maximum matching. That's it. That's your polynomial time algorithm for maximum flow. And that's it for today. Thanks. Hello everybody. Welcome to our course in Discrete Mathematics and welcome to our second session on matchings in bipartite graphs. Today I will prove Holtz's theorem and some other classic theorem from graph theory which is called Koenig's theorem. Let's quickly repeat the key notions from last time. We defined what a matching is. A matching is a set of edges. Here in this picture it's the blue edges. And for a set of vertices on the left-hand side of the bipartite graph, we defined what the neighborhood is, gamma of A. And for a set A, we defined the deficiency of A to be delta A, which is A minus the size of its neighborhood. And delta of G is the maximum over all subsets A on the left-hand side. And with this setup, we can state Holtz's theorem. It has two parts, the easy and hard part. The easy part says the matching cannot be bigger than U minus delta A, and the hard part that we're going to prove today says you can actually find a matching in a set where these two numbers match, where these two numbers are the same. And put together, they form what you normally read as Holtz's theorem in the literature. Last time we also saw an algorithm for maximum matching, which drew heavily on our machinery developed over the last couple of sessions, namely maximum flow. Let's quickly go through it again. So you have a bipartite graph, you attach a source and a sinc vertex, and you find a maximum flow in your network, a maximum integral flow, and then you can extract your maximum matching. That's an algorithm based on network flow. All right. So we know how to efficiently find a maximum matching, and we know the easy part of Holtz's theorem, and we want to prove the hard part of Holtz's theorem today. That's the program for this session. But in order to do this, I want to introduce another important concept of graph theory, and this is called vertex cover. So again, we have a graph, for today a bipartite graph. And a vertex cover is a set of vertices that touches every edge. Formally, that's a formal definition. So let's now try to find a vertex cover in this graph. For example, you could say I take all the vertices on the left, and sure enough, I touch every edge. I can also take all the vertices on the left plus some vertices on the right. Now I have a vertex cover of size 10. Also. But the interesting question, of course, is how many vertices do I really need? For example, in this graph, let's see which vertices should we choose. So I could, for example, choose these 4 vertices, and you can check that this is really a vertex cover of size 4. And let's see whether this is optimal or whether we can do something better. So the important theorem about vertex covers in bipartite graphs, it's called Koenig's theorem. And just like Holtz's theorem, it comes with an easy part and a hard part. The easy part says if you have a vertex cover in a matching, then the vertex cover must be at least as large as the matching. And this is kind of easy to see. If I have a matching like this, what is a matching? A matching is a set of edges that don't touch each other. And now I want to select a set of vertices that touches every edge. Well, I also have to touch every edge in my matching, and every vertex can only touch one of them because they're disjoint, right? So you immediately see I need at least as many red vertices as I have blue edges here. The hard part of Koenig's theorem says that these two numbers can actually match. So if you find an optimal vertex cover and an optimal matching, their sizes will be equal. For example, in this graph up here, that's our vertex cover. Yeah, and where's our matching? Let's find a matching of size. This edge, maybe this edge, and this edge. Right? So you see here you have a matching of size 4 and you have a vertex cover of size 4, and this immediately implies that it's a minimum vertex cover and a maximum matching. So now our goal is to prove the hard part of Koenig's theorem. Oh, first of all, if you combine these two, the version you find Koenig's theorem in the literature usually is in the following form here. In a bipartite graph, the maximum matching has the same size as a minimum vertex cover. Also note that here I forgot this. So it's Koenig's theorem, not Koenig's theorem or something. Good, let's try to prove the hard part. So what do we want to do? We want to find a vertex cover and a matching of the same size. Let's try. So here's our bipartite graph, and just as in the algorithm, I add a source vertex S and a sink vertex T. Okay. So if you remember the algorithm actually was to search for a maximum flow, maximum integral flow, and then you can immediately extract the matching from it. So the maximum matching has the same size as the maximum flow. All right, so what do we know about maximum flow? Well, we know the max flow min cut theorem. So we know that this equals the capacity of a minimum cut. A minimum ST cut. This is a fact that we just import, that we take from 2 lectures ago, 3 lectures when we proved it, and we are going to apply it today. So S is an ST cut, which means that S contains the source but not the sink. So it must somehow look like this. That's our set S, the minimum cut. Now consider this set here and call it A, and this set here and call it B. So formally A is S intersect U and B is S intersect V. And here comes a key observation. Suppose you have a vertex X here and a vertex Y here. So what happens if you have an edge from X to Y? So if XY is an edge, well then the capacity of your cut must be at least the capacity of this edge, right? Because this edge goes from S to its complement. And what is the capacity of these edges? Well, we define this to be infinity. The edges that go between U and V in our flow network have capacity infinity. But you know, now you see this is a contradiction because the capacity of S equals the size of the maximum matching, and the maximum matching cannot be larger than, for example, the set U. So this is a clear contradiction. Let's mark kind of a big red arrow here. That's a contradiction, and thus we conclude for all x in A and y in V minus B, there is no edge xy. In other words, U without A together with B is a vertex cover. Right? It's a vertex cover of your bipartite graph. Let's give it a name, C. And what is the size of C? The size of C is U without A plus B. So let's compare this to the size of our matching. As we have seen, the size of the matching equals the value of the maximum flow, which by the Max-Flow-Min-Cut theorem equals the capacity of the cut. And what is the capacity of the cut? For this we have to look at the edges that go from S to its complement. So for example, edges like this that go from the source into here, they have capacity 1, and their total capacity is U without A, right? So now we don't have edges like this because our graph is bipartite, right? And we don't have edges like this, and we don't have edges like this by our above observation. So the remaining edges that go from S to its complement are actually edges going directly into T. And how many are there? Well, there are B many of them, and they all have capacity 1. And now you see here, very nice, the capacity of S is U minus A plus B, which happens to be exactly the size of our vertex cover. And there you go. This proves the hard part of Koenig's theorem. We constructed a matching and a vertex cover of the same size. Great. But it's even better because now we can, with no additional cost, actually finish the proof of Holt's theorem. Let's look for a second at this fact here. It tells you there is no edge from A to V without B. In other words, all the edges that go out of A are contained in B. So in other words, the neighborhood of A is contained in B. And with this fact, we can now lower bound the size of M as follows. We have just calculated the size of M is U minus A plus B. But now we know that B is larger than the neighborhood of A, at least as large. So we get this is U minus A plus gamma of A. And this is exactly U minus the deficiency of A. And this is exactly the hard part of Holt's theorem. We have a matching and we have a set A such that M is at least U minus delta A. All right, to wrap up, here is Koenig's theorem that we just have proved and Holt's theorem. These are two classic theorems from graph theory. The nice thing is, once you understand maximum flow and the Max-Flow-Min-Cut theorem, both of these theorems follow more or less painlessly. And actually, if you look into the literature or on Wikipedia or anywhere, in most cases, Holt's theorem is stated a little bit different. It's stated like this. If every set A has a neighborhood gamma of A that is at least as large as A, then you find a matching of size u. That's how it's usually stated. You can think about it, it is actually equivalent to the version of Hall's theorem as we stated it here. And one last thing, we talked only about bipartite graphs here, and for a good reason, because in general graphs, Koenig's theorem is simply not true. Let me give you an example. Here is a non-bipartite graph. And if I ask you, what is the maximum matching? It's obviously 1, because you can choose at most one edge. How about vertex cover? The smallest vertex cover has size 2 because you have to select at least 2 vertices. So you see here, already for the triangle, Koenig's theorem is not true anymore. And this actually has a deeper reason that comes from complexity theory. Let me tell you, so on the one hand side, if we are in general graphs, we can still find a maximum matching in polynomial time. So we have this algorithm, it's called Edmonds-Blossom algorithm, which finds a maximum matching in general graphs. But we don't know how to find a minimum vertex cover. And most researchers actually believe that this is impossible because vertex cover is something that is called NP-complete in complexity theory. And right, I mean, most people are very pessimistic about NP-complete problems and don't believe that we'll ever find an efficient algorithm for these problems. All right, actually, you have to turn it the other way around. The reason vertex cover, although it's NP-complete for general graphs, happens to be easy for bipartite graphs is because you have Koenig's theorem. And Koenig's theorem tells you can compute a maximum matching or you can compute this maximum flow. And then from this you can construct an optimal vertex cover. So in bipartite graphs, we just are lucky by Koenig's theorem and can find optimum vertex covers. All right, that's it for today. Thanks. Hello everybody, and welcome to the last session of this course. Thank you all for staying with the course for so long. In this last session, I don't want to start a whole new topic, obviously. In some way, we will go back to the very beginning of this course and again talk about a concept that we introduced back then. This is the concept of partial orderings. In some other way, this session is also a continuation of the last two ones because we will use what we have learned. We will use bipartite graphs and Koenig's theorem about matchings and vertex covers to prove a very cool theorem about partial orderings. Let's quickly repeat some key notions about partial orderings. Many weeks ago, we defined width and height. So here you see two examples of a partial ordering. And we defined the height of an ordering to be the size of the longest chain. So here the height would be 6. And here it would be 3. And similarly, the width is the size of the largest anti-chain. So this one has a big anti-chain, 8 vertices. So this partial ordering has width 8. All right, so this is width and height. And maybe you remember we proved the following theorem. It's called Mirsky's theorem. What it basically says is, here I drew the longest chain, here on this side. And on the right side, I drew the most efficient partitioning into anti-chains. And the theorem states that these numbers actually match. So now, if you remember the proof was pretty straightforward. Imagine this is your partial ordering, and you look for the maximal elements in the ordering, and then you chop them off. Then you get kind of an induced ordering on whatever is left. And again, you take your maximal elements and you chop them off. So basically, like a potato, you do tuk, 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 tuk. And whatever you chop off is the set of maximal elements, so it is an anti-chain. And this will actually give you the picture you get on the right-hand side. And then it is pretty immediate to see that there is actually also a chain of the same length. Something that I mentioned back then when we first talked about orderings, but that we didn't prove so far, is Dilworth's theorem, which is like the big brother of, it's the evil twin brother of Mirsky's theorem. It says basically the same, just with the terms chain and anti-chain switched. So here on the left, you see the largest anti-chain, and on the right, you see a partition into as few chains as possible, and the theorem assures that these two numbers again match. So how would you prove this theorem? Well, naively, you could again say, well, we take our ordering, but now instead of chopping off the maximal elements, we chop off the leftmost elements. Right? Just inspired by this picture that you see here on the screen. But this is, of course, nonsense, because what is the leftmost element? I mean, if you, for example, here, I mean, there is kind of a northernmost point, right? It's here, right? But what is the easternmost point on Earth? It just, it doesn't exist. Also, in orderings, to speak about the leftmost part doesn't make sense at all. So we probably cannot take the proof of Mirsky's theorem and slightly adapt it and get a proof for Dilworth's theorem. Doesn't work. We have to use more advanced tools, and luckily one of the tools is exactly what we proved last time. It's called Koenig's theorem. So today what we are going to prove is Dilworth's theorem, and let me slightly rephrase it into what I call is the qualitative version. It just says you can find an anti-chain in a partition into chains such that every chain intersects the anti-chain in exactly one element. Koenig's theorem stated that in bipartite graphs, the maximum matching has the same size as a minimum vertex cover. And also this, I want to reformulate in a qualitative fashion that doesn't talk about the size of things. So here it is, the qualitative version. It says there is a matching and a vertex cover, and there is basically a one-to-one correspondence between the vertex cover and the matching. You can read through this formal statement for as long as you want. Let me just show you a picture. So here you have a matching of 4 edges and you have a vertex cover of 4 vertices. But the qualitative statement is that every edge is incident to exactly one red vertex and every red vertex is incident to exactly one blue edge. Right? That's a qualitative statement of Koenig's theorem. Now what we are going to do, we're going to prove Dilworth's theorem using the qualitative version of Koenig's theorem. I kind of do proof by example now. So suppose we have this partially ordered set on 7 elements. What I drew here is actually the Hasse diagram. So if I want to draw all pairs of comparable elements, it would kind of look like this, right? Because also A is less than G by transitivity. So this is a graphical representation of our partially ordered set. It is a directed graph, right? Okay. And somehow we have to make this into a bipartite graph because we want to apply Koenig's theorem. So here's how we do it. We take our set, our partially ordered set, and we take a copy of it. So here we have A to G, and down here we have A prime to G prime. And then we define the edge set as follows. Whenever there is an edge, for example, here you see there is an edge from A to C, we introduce an edge from A to C prime down here. And we do this for every edge in the graph up here. Let's say this is the graph G, this is the graph G prime. So in all, it will look like this. It's kind of a mess, but anyway. All right. So what can we say about vertex covers and matchings? So first of all, let's apply Koenig's theorem to the bipartite graph. It says there is a vertex cover and a matching. And the matching looks like this. A is matched to C prime. C is matched to F prime, so it goes like this. B is matched to D prime. And D is matched to G prime. All right, this Koenig's theorem guarantees me the existence of such a vertex cover in the matching, where they're basically, you can imagine like every vertex is married to an edge in the matching and vice versa. All right, so what does that mean for the original graph, for the partial ordering? The first observation is your vertex cover is also a vertex cover in the original graph G. So let's say this is G, this is G prime. So what do I mean by that? Well, I mean if you take the vertices of your vertex cover A, B, and then F prime, G prime, but now upstairs there is no F prime, G prime, so we just take these vertices. You can see that this is also a vertex cover of G. And now define A to be V without C. So whatever is left is A. The first observation is A is an anti-chain. A is an anti-chain because C is a vertex cover. Well, I'll let you think about this, why this is actually a true statement. Second, look at the matching M. Now for each edge in the matching, let's draw this edge in the original graph G. So for example, we have an edge from A to C prime. So let's insert an edge here. And from C, there is an edge to F prime. So let's do an edge here. And from B to D. And from D to G. And now you see that these edges, they form paths in your ordering. And these are chains. So here is your partition into chains. This is a chain. This is a chain. And this is a chain. And now here is the key observation. Every edge E in M introduces one red vertex, right? And every red vertex is introduced by a matching edge. That's the qualitative statement of Koenig's theorem, right? But now if you look at a chain here at one of these paths, For example, this one has 2 edges, so it has 3 vertices, right? A path has 1 vertex more than it has edges. Or this here has 0 edges and it has 1 vertex. This has 2 edges and it has 3 vertices. Which means for every chain, there is at least one element that is not colored red, that is not in C. So let's write this down. For every chain, one element at least one element is not in C. Thus, it is in A. And therefore, your chain Ci intersect with A has size at least 1, but actually it cannot have size more than 1, so it has size exactly 1. And this is exactly the qualitative version of Dilworth theorem. So to wrap it up, we proved Dilworth theorem by showing first its equivalent to the qualitative Dilworth. And we proved this from the qualitative version of Koenig's theorem, which you can actually show to be equivalent to the Koenig theorem as we proved it last time. And how did we prove Koenig's theorem? Well, there was probably the longest proof that was from the Max-Flow-Mincutt theorem. Max-Flow-Mincutt. So we proved Koenig's theorem using the Max-Flow-Mincutt theorem, and the nice thing was that on the way to the proof, we actually also were able to prove Hall's theorem. Right, so kind of the tree of proofs that we did in the last couple of sessions looks like this. And it is actually a nice exercise to see that Koenig's and Hall's theorem are actually equivalent in the following sense. You can prove one from the other without going through the Max-Flow-Mincutt theorem. A little bit food for you is the following. The Wikipedia page of Dilworth theorem actually claims that from Dilworth theorem you can prove Koenig's theorem. So they actually claim that when you have Dilworth theorem you can prove Koenig's theorem, but I'm not convinced. I'm not convinced by the proof. So maybe I made a mistake, maybe the proof is fine, but if you want, go on Wikipedia and read through the proof and see whether it convinces you. That's it for today. Thank you all very much for today and for the whole semester. I hope you enjoyed it. I enjoyed it a great deal. Thank you very much.